What lies beyond everything we know? If the universe is expanding, what is it expanding into? These are not abstract philosophical musings, but questions born directly from observation and measurement. In 1929, Edwin Hubble identified that galaxies were not simply moving through space, but that the space between them was stretching. Redshift data revealed recession speeds proportional to distance, a discovery that overturned centuries of assumptions about a static cosmos. Today, precise measurements from the Hubble Space Telescope and the Planck satellite tell us that distant galaxies are receding at rates exceeding 70 kilometers per second per megaparsec. On the larger scales, clusters of galaxies millions of light-years away are moving apart at astonishing velocities, yet this motion is not into pre-existing emptiness. Instead, space itself is expanding. To explore this fully, cosmologists turn to relic signals from the earliest moments of time. The cosmic microwave background, first detected in 1965, shows us light that has travelled for nearly 13.8 billion years, stretching as the universe expanded, cooling from thousands of degrees to just 2.7 Kelvin today. This radiation fills every direction, a measurable reminder that space has been enlarging continuously since the Big Bang. Yet even with this wealth of data, the puzzle remains. If nothing exists outside the universe, how can expansion have any direction or destination? The very wording of the question reveals the challenge. Our everyday experience is shaped by objects growing into pre-existing space. An inflating balloon fills the surrounding air, a wave spreads across the surface of the sea. But when cosmologists describe the universe, they emphasize that expansion is not movement into emptiness. It is the metric of space itself increasing, the distances between points changing without any external container. Still, human intuition resists this explanation, leading us to ask again and again, if the universe has no outside, what exactly is expanding and what lies beyond? The story begins with the Big Bang, not as an explosion in space, but as the rapid emergence of space itself. According to measurements refined over decades, the event occurred approximately 13.8 billion years ago. Evidence supporting this date comes primarily from observations of the cosmic microwave background by satellites such as WMAP in 2001 and Planck in 2012-2009. These missions measured tiny variations in temperature across the sky, mapping conditions just 380,000 years after the universe's origin. That map confirms that the universe began in a state of extraordinary density and heat, then expanded and cooled into the cosmos we now observe. When physicists speak of the Big Bang, they do not mean a single explosion flinging material outward into emptiness. Instead, they describe a sudden event in which all of space came into being everywhere at once. At the very earliest fraction of a second, conditions were extreme beyond laboratory reproduction. The universe was smaller than an atom, yet it contained all the matter and energy that would form stars, galaxies, and clusters. In that brief moment, fundamental forces that govern reality began to separate. First gravity, then the strong nuclear force, followed by the electromagnetic and weak nuclear forces. These transitions, happening within trillionths of a second, set the blueprint for everything to come. One of the most striking aspects of the Big Bang is that time itself appears to have begun with it. Einstein's equations, when run backward, show that space and time both converge toward this origin. Asking what happened before the Big Bang may therefore be meaningless in the conventional sense. If time is part of the fabric that emerged, then before is a concept with no reference point. This conclusion challenges intuition, because every human experience is anchored in sequences of time, yet the equations are consistent, and so far no observation has contradicted them. Within the first second of existence, the universe underwent rapid cooling. At roughly 1 second after the Big Bang, it was about 10 billion degrees Kelvin, a temperature high enough to prevent atomic nuclei from holding together. Instead, particles like protons, neutrons, electrons, and neutrinos streamed freely. As expansion continued, temperatures dropped, and by about 3 minutes, conditions allowed hydrogen and helium nuclei to form through processes of nuclear fusion. Astronomical observations of elemental abundances today, nearly 75% hydrogen, 25% helium by mass, with trace amounts of lithium, match precisely with these theoretical predictions. This agreement provides one of the strongest confirmations that the Big Bang model reflects reality. The most mysterious stage of this early history is cosmic inflation, a theory first proposed in 1981 by Alan Guth. Inflation suggests that in less than a trillionth of a second after the Big Bang, the universe expanded faster than the speed of light, growing from subatomic size to astronomical scale almost instantaneously. This idea, though counterintuitive, is supported by evidence. The uniformity of the cosmic microwave background across vast distances implies regions once connected were stretched apart too quickly for light to ever pass between them again. Inflation provides a mechanism for this, explaining why the universe appears smooth on large scales, while still containing small variations that later seeded galaxies. But if inflation occurred, the question deepens. What triggered it, and what did it expand into? Current models suggest inflation was driven by a hypothetical energy field, sometimes called the inflaton. As the field decayed, it released energy that filled the universe with particles and radiation, yet no experiment has directly confirmed the inflaton's existence. Without that confirmation, scientists must rely on indirect signatures, such as patterns in the polarization of the cosmic microwave background. Observatories like BICEP at the South Pole have searched for these signals, but results remain inconclusive, keeping the debate open. The Big Bang model successfully describes how the universe evolved from its earliest moments, yet it also leaves boundaries of knowledge clearly exposed. We can trace conditions back to the first 10 to the minus 43rd seconds, the Planck time, beyond which our physical theories break down. At that scale, quantum effects of gravity become significant, and general relativity is no longer sufficient. A complete theory of quantum gravity would be required to push further, but such a framework remains unfinished. This limitation means that although we can describe the unfolding universe from an incredibly early point, the absolute moment of origin, if it can be defined at all, lies outside our current understanding. The narrative of the Big Bang challenges our sense of what expansion really means. If space itself was created in that moment, then the universe was never inside something larger. It was always self-contained, with no external backdrop. Yet the mind resists such an idea. We picture expansion as a balloon swelling into surrounding air or a shockwave racing outward. Cosmologists insist that such images are misleading, because there is no external arena for the universe to occupy. Still, the analogy is useful for one reason. It helps explain how galaxies can appear to rush away from one another without moving through space, but rather carried apart as space stretches between them. Measurements today show that this process continues. Galaxies beyond our local group are receding, with speeds increasing in proportion to their distance. A galaxy 1 megaparsec away moves away at about 70 kilometers per second. A galaxy 2 megaparsecs away recedes at 140 kilometers per second. At extreme distances, recession speeds surpass the speed of light, not because galaxies move faster than light, but because space itself expands between us at that rate. This observation demonstrates that the rules of everyday experience cannot be directly applied to the universe as a whole. The Big Bang, then, is not a story of matter flung into a void, but of space-time itself opening, stretching, and cooling. The evidence is clear in elemental abundances, in the cosmic microwave background, and in the recession of galaxies. Yet the core mystery lingers. If expansion is intrinsic to space, if time itself began with the event, then the question remains. When we say the universe expands, into what does it expand? And does the very structure of reality allow that question to be meaningfully answered, or does it point us toward a limit in how human thought can grasp existence? To understand the expansion of the universe, astronomers look not only at galaxies rushing apart, but at the oldest radiation still visible, the cosmic microwave background. Discovered accidentally in 1965 by Arno Penzias and Robert Wilson, while working with a radio antenna at Bell Labs in New Jersey, this faint signal fills the sky uniformly in every direction. Its temperature is measured at about 2.725 Kelvin, just a fraction above absolute zero. Yet this radiation is not noise. It is the cooled remnant of the time when the universe first became transparent, nearly 380,000 years after the Big Bang. Before that moment, matter was so hot and dense that photons scattered constantly off free electrons, preventing light from travelling freely. As the universe cooled, electrons combined with protons to form neutral hydrogen in a process called recombination. At that instant, photons decoupled from matter and began their uninterrupted journey across expanding space. When we detect the cosmic microwave background today, we are seeing those ancient photons stretched by expansion from high-energy visible and infrared light down to microwave wavelengths. The measurements confirm that the universe was once hot, dense, and uniform, with only tiny fluctuations. These fluctuations, just one part in 100,000, appear as faint temperature differences across the sky. They may seem trivial, but they are crucial. Over billions of years, gravity amplified them into the vast cosmic structures we now observe, galaxies, clusters, and filaments stretching across the observable universe. The first detailed maps of this background came from the COBE satellite in 1989, which revealed the faint anisotropies that theory predicted. Later missions such as WMAP in the early 2000s and Planck in 2009 provided sharper data, measuring temperature differences with microkelvin precision. The results allowed cosmologists to determine key parameters: the age of the universe, its composition, and its geometry. Planck data showed that ordinary matter accounts for less than 5% of the cosmic budget, with dark matter contributing about 27% and dark energy making up nearly 68%. These proportions explain the observed pattern of expansion, yet they also highlight that most of the universe remains fundamentally mysterious. The microwave background also carries information about the universe's shape. By studying the angular size of fluctuations across the sky, scientists can infer whether space is curved like a sphere, saddle-shaped, or flat. The data suggest remarkable flatness on cosmic scales, with deviations smaller than a fraction of a percent. This flatness raises further questions, because without an early mechanism like inflation, the universe would not naturally evolve into such a balanced state. The consistency across billions of light-years suggests that the inflationary phase smoothed out any initial curvature, leaving a geometry that remains nearly flat today. Another aspect revealed by microwave observations is the presence of acoustic oscillations, sound waves rippling through the plasma of the early universe. These oscillations froze into the matter distribution when photons decoupled, leaving behind a characteristic scale visible in the cosmic microwave background and in the large-scale distribution of galaxies today. Known as baryon acoustic oscillations, this scale provides a standard ruler that cosmologists use to measure expansion history with precision. It is a bridge connecting the universe we see now with conditions just hundreds of thousands of years after its origin. Yet the cosmic microwave background does more than confirm theories. It also challenges them. The data show slight anomalies, such as hemispherical asymmetry and unexplained alignments, sometimes called the axis of evil. These irregularities are statistically weak but persistent across different measurements. They raise the possibility that the universe's early conditions may not be perfectly explained by standard inflationary models. Some researchers suggest these features might point to new physics, perhaps hints of structures beyond the observable universe. Others argue they may simply be random fluctuations magnified by human pattern recognition. Either way, they remind us that even the most carefully measured data can leave room for interpretation. The cosmic microwave background is not static. As the universe continues to expand, the radiation cools further, its wavelength stretching into longer bands. In the distant future, trillions of years from now, it will shift so far into radio frequencies that it will become undetectable by any conceivable observer. At that point, the clear evidence of the Big Bang will fade, leaving future civilizations with fewer clues about cosmic origins. We living now occupy a privileged epoch in which the signal is both strong and accessible, allowing us to reconstruct the earliest history of the cosmos with remarkable accuracy. This knowledge has not only shaped cosmology, but transformed our view of existence. For centuries, humans debated whether the universe was eternal and unchanging. The discovery of the cosmic microwave background offered decisive evidence that the cosmos had a beginning in time, that it was once unimaginably hot and dense, and that it has been cooling and expanding ever since. No other theory explains this background so directly. Competing models of a steady-state universe, once popular in the mid-20th century, could not account for this omnipresent relic radiation. The uniformity and black-body spectrum of the background matched predictions of the Big Bang theory, with striking precision, solidifying expansion as a central fact of modern science. The microwave background also gives us a way to measure the rate of expansion with great accuracy. By comparing its fluctuations to the distribution of galaxies and supernovae, scientists refine estimates of the Hubble constant. Yet here lies a modern puzzle. Measurements from the early universe using Planck data give a slightly lower value of the Hubble constant than measurements from nearby galaxies using the Hubble Space Telescope and other observatories. This discrepancy, known as the Hubble tension, has become one of the most pressing issues in cosmology. It may indicate that our models of cosmic expansion are incomplete, perhaps requiring new physics such as evolving dark energy, interactions in the dark sector, or modifications of general relativity itself. Efforts to probe deeper continue. Scientists are developing instruments to measure the polarization of the cosmic microwave background with extreme precision, searching for subtle patterns left by primordial gravitational waves. Such a discovery would provide direct evidence of inflation, a rapid expansion in the first tiny fraction of a second after the Big Bang. Experiments like BISEP at the South Pole and future space missions are designed to push the limits of detection. A confirmed signal would not only extend our knowledge closer to the very beginning, but also illuminate physics at energy scales far beyond what particle accelerators can reach. But one question persists. If this background light shows us a universe already hundreds of thousands of years old, what happened in the interval before recombination? What processes unfolded in those earlier moments that we cannot see directly? Observations of the cosmic microwave background provide a boundary of knowledge, a wall of radiation beyond which light cannot penetrate. To reach earlier times, scientists must turn to indirect traces, such as neutrinos or gravitational waves, which could carry information from the first second, or even earlier. Efforts to detect a gravitational wave background from inflation are ongoing, with experiments at the South Pole and space-based observatories planned for the future. If successful, they could extend our vision closer to the very beginning. The cosmic microwave background therefore anchors our understanding of expansion. It demonstrates that space itself has been stretching for nearly 14 billion years, cooling radiation as it goes. It shows that the universe has no preferred center, that every observer sees the same faint glow, and that expansion is not into emptiness, but of space itself. It proves that the cosmos is governed by laws that can be measured, tested, and refined. Yet as with every step in cosmology, these answers generate further puzzles. If the universe is flat, smooth, and expanding everywhere, what mechanism sustains this expansion across such vast scales? What forces balance the delicate structure we observe today? And how did astronomers first realize that galaxies themselves held the key to this mystery? The turning point came in the late 1920s, when astronomer Edwin Hubble was working at Mount Wilson Observatory in California, using the 100-inch Hooker telescope, the largest in the world at that time. Hubble's task was to measure the distances to faint spiral nebulae, objects whose true nature was still under debate. Some astronomers believed these spirals were relatively small and located within our own Milky Way. Others suspected they were immense and distant systems in their own right. The debate was settled when Hubble identified Cepheid variable stars within these spirals. Cepheids have a known relationship between their brightness and their pulsation period, making them reliable standard candles for distance measurement. By observing these stars, Hubble demonstrated that spiral nebulae like Andromeda were far outside the Milky Way, confirming they were separate galaxies. This revelation already reshaped human understanding, but Hubble went further. Working with Vesto Slipher's earlier spectroscopic data, he noticed a striking pattern. The light from these galaxies was shifted toward longer, redder wavelengths, a redshift. At first, such shifts were interpreted as Doppler motion, meaning the galaxies were moving away through space. But as Hubble compiled data on dozens of galaxies, he found a linear relationship. The greater the distance, the greater the redshift. Published in 1929, this finding became known as Hubble's law. It suggested not random motion, but a systematic expansion of the universe itself. The implications were immense. Rather than galaxies flying outward into pre-existing void, the interpretation was that space itself was stretching, carrying galaxies with it. Imagine dots on the surface of a balloon. As the balloon inflates, the dots all move apart, though none is travelling through the surface. This analogy, while imperfect, captured the essence of what Hubble had uncovered. The expansion was not relative to a central point, because every galaxy observed sees all others receding. The universe, on large scales, has no special location or edge. Hubble's discovery was initially met with skepticism. Albert Einstein, who had formulated general relativity in 1915, had originally modified his equations with a cosmological constant to maintain a static universe, which he believed to be the natural state of things. When confronted with evidence of expansion, Einstein reportedly called his adjustment the greatest blunder of his life. He later accepted that his own theory, unaltered, already predicted a dynamic cosmos. General relativity allowed space itself to expand or contract, depending on the balance of matter and energy. Observations confirmed that expansion was real, not theoretical. Subsequent measurements refined the rate of expansion, now known as the Hubble constant. Early estimates varied widely, from 50 to 500 kilometers per second per megaparsec, due to uncertainties in distance calibrations. Over the decades, better instruments narrowed the range. The Hubble Space Telescope, launched in 1990, played a critical role in measuring Cepheids with unprecedented precision. More recently, Type Ia supernovae, stellar explosions with consistent peak brightness, have become additional standard candles. Combining these methods yields values around 70 kilometers per second per megaparsec, although some tension remains between results from different techniques, a discrepancy now called the Hubble tension. The expansion revealed by Hubble is not merely an observational curiosity, but the foundation of modern cosmology. It confirms that the universe had a finite beginning, aligning with Big Bang models. It explains why the cosmic microwave background is stretched to microwave wavelengths. It provides the framework for calculating distances and ages, for mapping cosmic structure, and for estimating the universe's fate. Without Hubble's work, the notion that the cosmos is dynamic, evolving, and vast might have remained hidden. Yet with this discovery came deeper questions. If galaxies recede in every direction, does that imply the universe is expanding into something external? The balloon analogy offers a partial visualization, but does not resolve the puzzle. The surface of a balloon is two-dimensional but embedded in three-dimensional space. For the universe, no such higher dimensional container is required. General relativity describes expansion without an outside, defining the metric of space itself. Still, the human mind insists on imagining a boundary, a frontier beyond which expansion proceeds. Reconciling these intuitions with the mathematics remains one of the most challenging aspects of grasping cosmic expansion. The power of Hubble's discovery lies not only in the evidence it provided, but also in the perspective it forced. Humanity shifted from seeing a static, eternal universe centered on our own galaxy to recognizing a dynamic cosmos, uniform and boundless on the larger scales. Every point participates equally in expansion. Every observer sees the same recession pattern. This universality is central to the cosmological principle, the idea that the universe is homogeneous and isotropic when viewed on sufficiently large scales. Still, the pattern of redshifts left a mystery. Why is expansion happening at all? What mechanism drives it, and what determines its rate? To answer these questions, cosmologists developed the theory of inflation, a brief but extraordinary burst of expansion in the earliest instant of time. Inflation solves puzzles of uniformity and flatness that Hubble's discovery alone could not explain. But the idea of inflation raises its own difficult questions, including what exactly expanded during that phase, and whether expansion could extend beyond our observable horizon into regions forever beyond reach. The galaxies receding from us are not vanishing into emptiness, but retreating across a growing fabric of space-time. The farther we look, the faster they appear to recede, until at extreme distances their light never reaches us. This fact ties the observable universe to a finite boundary, not because the universe ends, but because expansion outpaces light. This horizon defines the edge of what we can see, not the edge of all that exists. The link between redshifts and cosmic horizons open the door to deeper questions about what can be known and what forever lies outside our view. The shift brought by Hubble's work also transformed the way scientists approached cosmology as a whole. Before his discovery, cosmology had been largely speculative, driven more by philosophy than by observation. With redshifts and distances, the universe became quantifiable. Expansion could be measured, modelled, and tested against predictions of general relativity. It became a science rooted in data rather than conjecture. Each new observation reinforced the central truth that the universe evolves with time and that its structure and fate are determined by physical processes measurable in principle. In the decades following Hubble's announcement, astronomers built ever larger surveys, mapping thousands and then millions of galaxies. Each confirmed the same trend: galaxies recede faster the farther away they are. Superclusters, voids, and filaments all trace the imprint of expansion. The observational universe grew not only in size but in detail, showing structure on scales unimaginable in Hubble's era. His law proved universal, a cornerstone upon which modern cosmology continues to stand. Still, the Hubble law left gaps that modern science has yet to close. One puzzle is the precise value of the Hubble constant, where tensions between early universe and late universe measurements may point toward new physics. Another is the origin of the expansion itself. What launched it? Was it simply the initial condition of the Big Bang, or does expansion require an ongoing mechanism sustained by dark energy? These questions drive some of the most ambitious projects in astronomy today, from the James Webb Space Telescope to surveys mapping baryon acoustic oscillations across billions of light years. Hubble's discovery was therefore not an endpoint, but a beginning. It laid the foundation for the next century of cosmic investigation, showing that the universe is neither eternal nor static, but dynamic and evolving. Each new generation of telescopes has sharpened the picture, yet the core truth remains: galaxies are carried apart not by motion through pre-existing space, but by the expansion of space itself. This fact challenges intuition, but defines reality. It ties the observable cosmos to general relativity, to the physics of the early universe, and to the unsolved mysteries of dark energy. And as the galaxies recede across horizons we cannot cross, one question grows sharper. If the universe is expanding everywhere at once, with no center and no edge, what exactly is expansion acting upon? Is there truly nothing outside, or does expansion hint at dimensions, structures, or realities beyond our perception? In the earliest fractions of a second after the Big Bang, the universe behaved in a way that challenges even the most advanced physics. Standard models of expansion could not explain certain observations. Why does the cosmic microwave background appear so uniform in every direction, even in regions of the sky that could never have exchanged light or information at the speed of light? Why does the geometry of the universe appear flat, when general relativity allows for curvature that should grow over time? Why are relics predicted by particle physics, such as magnetic monopoles, so conspicuously absent from the universe we see? In 1981, Alan Guth proposed a solution that became known as cosmic inflation. According to this theory, the universe underwent an extraordinary expansion in the first 10 to the power of negative 36 to 10 to the power of negative 32 seconds of its existence. In this unimaginably brief interval, space increased in size by a factor of at least 10 to the 26th power. To place this into perspective, a region smaller than a proton would have expanded to a size larger than a galaxy. This sudden and exponential growth would have stretched space so quickly that any initial irregularities were smoothed away, leaving the large-scale uniformity we observe today. The mechanism behind this process is theorized to be a high-energy field, sometimes referred to as the inflaton. While no direct evidence for such a field has been found, its existence is consistent with particle physics models that predict fields capable of storing and releasing enormous amounts of energy. During inflation, the energy of this field would have acted like a repulsive force, driving expansion faster than the speed of light. When the field decayed, it would have released its stored energy into a bath of particles and radiation, reheating the universe and continuing the standard Big Bang evolution from that point forward. One of the strongest arguments in favor of inflation is the horizon problem. The cosmic microwave background shows nearly identical temperatures across the sky, separated by vast distances. Without inflation, these regions could never have interacted because light had no time to travel between them in the early universe. Inflation solves this by proposing that these regions were once close together, able to exchange energy, before being driven apart faster than light by exponential expansion. What appears to us as distant and causally disconnected regions were, in fact, once neighbours. Another puzzle solved by inflation is the flatness problem. Observations show that the geometry of the universe is very close to flat, with parallel lines continuing without convergence or divergence across cosmic distances. But in standard cosmology, any slight curvature at the beginning would grow over time, leading to either rapid collapse or runaway expansion. Inflation flattens space in the same way a balloon inflates to smooth out wrinkles, leaving behind a universe that appears flat on scales we can observe. Planck satellite data confirming near-perfect flatness is one of the strongest indicators that something like inflation must have occurred. Inflation also explains why exotic relics predicted by particle physics, such as magnetic monopoles, are not observed. If such objects formed in the early universe, inflation would have diluted their density to near zero by spreading them across a vastly expanded space. Their absence is therefore not a contradiction, but an expected consequence of inflationary expansion. Beyond solving these puzzles, inflation provides testable predictions. One is that inflation should leave behind a distinct pattern of density fluctuations in the cosmic microwave background. These fluctuations arise from quantum variations in the inflaton field, stretched to cosmic scales by expansion. Over time, gravity amplified these tiny seeds into the large-scale structure of galaxies and clusters we see today. Observations of the microwave background confirm the predicted spectrum of fluctuations with remarkable accuracy. Another prediction is the existence of primordial gravitational waves, ripples in space-time produced during inflation. These waves would leave a signature in the polarization of the cosmic microwave background, specifically in a pattern called B-mode polarization. In 2014, a team working with the BISEP 2 telescope at the South Pole announced possible detection of this signal. However, the result was later shown to be contaminated by galactic dust. Searches continue, with new experiments like BISEP 3 and space-based missions planned to probe deeper into this elusive evidence. If detected, such a signal would be one of the most direct confirmations of inflation. Despite its successes, inflation is not without controversy. Critics argue that the theory is flexible enough to accommodate almost any observation, making it difficult to test definitively. Some versions predict eternal inflation, in which expansion never fully ends but continues in pockets, producing an infinite series of bubble universes with different physical properties. This leads directly into discussions of the multiverse, where our observable universe is just one region in a vast and perhaps unending ensemble. While mathematically consistent, these scenarios raise philosophical questions about what can be considered science if direct observation is impossible. Another unresolved issue is the nature of the inflaton itself. No particle or field corresponding to this role has been detected in laboratory experiments. High-energy particle physics, including work at the Large Hadron Collider, continues to search for clues. Without such a discovery, inflation remains a theoretical construct supported indirectly, but not directly observed. Still, inflation remains the leading explanation for the universe's earliest growth, widely accepted because it addresses so many otherwise intractable problems. It demonstrates that expansion is not simply a smooth process from the beginning, but may have included dramatic and violent stages that shaped everything we see today. The idea that quantum fluctuations in a microscopic field could be magnified to cosmic scales challenges intuition, but aligns with both relativity and quantum mechanics. If inflation did occur, then our observable universe is only a tiny fraction of the whole. The regions beyond our cosmic horizon, forever unreachable by light, may be vastly larger and possibly different in composition. Inflation forces us to confront the possibility that what we can see is not representative of the entire cosmos. Yet even with inflation as an explanatory framework, the question remains open. If the universe expanded so quickly and continues to expand today, does this imply an external realm into which space grows? General relativity insists no such external stage is required. Expansion is intrinsic to space-time itself, not motion into an outside. But if inflation may have produced other universes, each with their own space-time, then the concept of outside must be reconsidered. Is our universe just one bubble among many? And if so, what does it mean for expansion to occur within an infinite ensemble? The question of whether the universe has an edge arises naturally from the idea of expansion. When we hear that galaxies are rushing away from one another, it seems almost inevitable to imagine some cosmic frontier, a wall at the end of everything, a boundary beyond which lies nothing at all. The human mind, shaped by experience in a world of physical borders, walls, horizons, oceans, instinctively searches for an outermost edge. Yet, modern cosmology strongly suggests otherwise. The universe, according to the best evidence available, does not appear to have a physical edge. Its expansion is not the spreading of matter into a pre-existing void. Rather, it is the stretching of the fabric of space itself. This idea is profoundly counterintuitive because it forces us to abandon the notion of the cosmos as a thing expanding into something else. Instead, what expands is the internal geometry of reality itself. To approach this strange truth, cosmologists often turn to a simple but powerful teaching tool, the balloon analogy. Imagine the two-dimensional surface of a balloon, smooth and round, with tiny dots drawn upon it to represent galaxies. As the balloon inflates, the surface stretches, and the dots all move apart. Crucially, no dot is moving across the surface under its own power. Instead, the surface itself is expanding. Every dot sees all others receding, and none occupies a special center. Just so, in the universe, galaxies do not fly through space so much as space itself grows between them. But the analogy, though useful, is limited. The surface of the balloon is two-dimensional and embedded in the three-dimensional space of our world. We can easily point to the air around it as outside. The universe, however, is not thought to be embedded in a higher dimensional container, at least not in any way science has yet proven. Space itself is all there is. In this sense, asking what lies beyond the universe is like asking what lies north of the North Pole. The question dissolves upon reflection. Geometry provides another way to understand this. The universe can, in principle, be finite yet without an edge, depending on its curvature. On a sphere, for example, there is a finite surface area, but no point where the surface stops. Travel far enough in one direction, and you will eventually return to where you began. Likewise, if the universe is closed, its extent is limited, but it still has no boundary. Alternatively, if space is flat or open, it may extend infinitely in all directions. In neither case does there exist a cosmic wall. Modern measurements lend insight here. Observations of the cosmic microwave background radiation, particularly those made by the Planck satellite, suggest that on the largest scales the universe is astonishingly close to flat. This finding implies that space may very well be infinite, stretching without limit. Even if it is not infinite but merely extremely large and curved, its geometry prevents it from having an edge. What lies outside is not an applicable question, because relativity does not describe space as sitting within anything else. This also challenges the notion of a center. If expansion were like an explosion, it would be natural to expect one point of origin, with galaxies blasting outward from a central location. Yet this is not what we observe. Wherever you are in the universe, the galaxies appear to recede in every direction, with speeds proportional to their distance. Every observer, no matter where located, sees essentially the same pattern. This tells us that the Big Bang was not an eruption from a point in space. It was an event of space itself, everywhere, all at once. Every region of the cosmos was once compressed, and every region now expands. This understanding leads us to the concept of the observable universe. The light we see today has travelled to us over billions of years, limited by the finite speed of light and the finite age of the cosmos. This creates a horizon, a spherical boundary centred on us, marking the farthest distance from which light has had time to arrive. That horizon today lies about 46 billion light-years away, larger than the age of the universe in years because space has been stretching, even as light crossed it. Beyond this horizon, countless galaxies almost certainly exist, but they are forever invisible to us. Their light, stretched by expansion, will never reach Earth. Importantly, this horizon is not an edge. It is a limit of our visibility. Much as sailors of old could see only to the line of the horizon but knew the ocean continued beyond it, cosmologists recognize that what we can observe is only a fraction of the whole. Our horizon defines what is accessible to observation, not what exists. The difficulty lies in reconciling this scientific view with our human instincts. We live surrounded by boundaries, fences, coastlines, national borders. Our experience teaches us that every surface ends somewhere, that every volume is contained within something larger. To imagine a universe without such a limit stretches our intuition to its breaking point. The very concept of infinity, though mathematically precise, resists visualization. One way to ease this tension is to revisit the idea of curved space. Just as the surface of Earth is curved into 3 dimensions, our 3-dimensional universe might itself be curved into higher dimensions. If so, the universe could be finite but without boundary, much like a higher dimensional sphere. The expansion we perceive might then be interpreted as a change in that higher dimensional geometry. This idea resonates with some versions of string theory, which postulate additional dimensions beyond the familiar 3 of space and 1 of time. Yet, while intriguing, these ideas remain speculative. No experiment has yet revealed such higher dimensions. Even without invoking higher realms, general relativity provides the framework we need. In Einstein's equations, space-time itself is the arena of reality. Asking about an outside makes as little sense as asking what lies beyond mathematics. Space is not contained, it is the container. Expansion happens not into anything but within itself, by its own rules of curvature and energy. This absence of an edge has profound implications for cosmic destiny. If there is no boundary, then the universe will not end by crashing into a wall. Its fate depends instead on the balance of its contents: matter, radiation, dark matter, and above all, dark energy. As galaxies drift farther apart, stars burn out, and black holes evaporate, the universe changes not by reaching a limit but by transforming internally. The future might hold a heat death, where expansion dilutes all energy until nothing remains but cold emptiness. Or if dark energy grows stronger, the universe could accelerate into a big rip, tearing apart galaxies, stars, and even atoms. In each case, the story unfolds without a frontier. The cosmos does not collide with an edge, it simply evolves. In this sense, the absence of an edge deepens rather than diminishes the mystery. It shifts the focus from questions of boundaries to questions of geometry, energy, and time. It tells us that the universe is not a bubble growing in some larger void, but a fabric stretching according to laws that emerge from its own structure. And it leads us naturally to a deeper inquiry. If there is no edge, then what is it exactly that is expanding? That question brings us to curved space itself, and how understanding its properties may redefine not only what expansion means, but also what reality is. Curved space is not an abstract idea reserved for mathematicians or philosophers. It is a measurable feature of the universe, predicted by general relativity and confirmed through countless observations. In Einstein's framework, matter and energy do not merely sit within the stage of space, they shape the stage itself. Space-time is flexible, bending and curving in response to the presence of mass and energy. On Earth, we experience this curvature as gravity. When an apple falls from a tree, we think of it as being pulled downward. But in Einstein's view, the apple is simply following the straightest possible path, what physicists call a geodesic, through a space-time that is curved by Earth's mass. Our daily perception of weight, of orbits, of falling, is the manifestation of this geometry. And when we extend the same principle to the cosmos itself, the geometry of space defines the overall shape and destiny of the universe. To understand what this means, we begin with 3 broad possibilities. The universe could be closed, open, or flat. A closed universe has positive curvature, like the surface of a sphere. In such a universe, travelling far enough in one direction could eventually bring you back to your starting point, though in 3 dimensions rather than 2. Imagine a starship leaving Earth and flying endlessly forward, only to circle the cosmos and return from the opposite side. In this case, the universe would be finite in extent, yet it would have no boundary, no wall, no edge, because geometry itself closes back on itself. An open universe, by contrast, has negative curvature, similar to the shape of a saddle. In such a space, parallel lines eventually diverge. Distances grow faster and faster as one travels outward, giving rise to an infinite and ever-expanding cosmos. The third possibility is a flat universe, one with 0 curvature. In this scenario, parallel lines remain parallel forever, just as they do in ordinary Euclidean geometry. Space would stretch on in all directions without bending inward like a sphere or outward like a saddle. Which of these possibilities describes our universe depends on the balance between matter, energy, and the rate of expansion. In the mid-20th century, cosmologists debated fiercely which geometry matched reality. The outcome would determine not only the shape of space, but also the universe's ultimate fate. The decisive evidence came from the study of the cosmic microwave background radiation, the faint afterglow of the Big Bang, now cooled to just a few degrees above absolute zero. Satellites such as WMAP and Planck mapped tiny fluctuations in this radiation across the sky, encoding information about the universe's geometry. The results were astonishingly precise. The cosmos is flat to within a fraction of a percent. This flatness implies that, on the larger scales, space does not curve back on itself like a sphere, nor does it splay outward like a saddle. Instead, it stretches evenly in all directions, consistent with the familiar rules of geometry we learn in school. Yet this simple outcome has profound implications. The fact that the universe is so close to flatness is one of the strongest confirmations of inflationary theory. The idea that in the first tiny fraction of a second after the Big Bang, the universe underwent an unimaginable burst of exponential expansion. This rapid inflation smoothed out any initial curvature, leaving behind the nearly flat cosmos we observe today. But flatness does not mean simplicity. Even in a globally flat universe, local curvature occurs around massive objects. Every galaxy, every star, every cluster bends space-time in its vicinity. We see the effect most clearly in gravitational lensing, where the light of distant galaxies is stretched and twisted by the gravity of intervening matter. Astronomers use this lensing to map invisible structures, revealing the vast scaffolding of dark matter that permeates the cosmos. These distortions are not illusions, but direct evidence that space itself is curved, and that light, though it always travels straight, follows the bends and folds of geometry. This interplay between local curvature and global flatness gives rise to the cosmic web, a network of filaments and voids stretching across billions of light years. Gravity pulls matter into knots and strands, while expansion stretches the fabric between them. What results is not chaos, but structure. Clusters of galaxies linked like beads on invisible strings, surrounded by immense empty regions. Geometry does more than shape structure, it dictates destiny. In a closed universe, expansion might one day halt, giving way to contraction and an eventual big crunch, where everything collapses back into a singular point. In an open or flat universe, expansion continues indefinitely, though the speed and manner of that expansion depend on the balance of energy. For much of the 20th century, cosmologists asked whether the cosmos contained enough matter to reverse expansion. Was the universe doomed to collapse, or would it drift apart forever? The discovery of dark energy in the late 1990s transformed the debate. Observations of distant supernovae revealed that expansion is not slowing down but accelerating. Space is stretching faster with time, pushed apart by an energy whose nature remains mysterious. This means that even in a flat universe, expansion will not gradually taper off into a slow drift. Instead, galaxies will continue racing away from one another at ever-increasing speeds. The long-term fate of the cosmos is not a crunch, but a cold, empty future, or perhaps something even stranger. Curvature also forces us to rethink the very meaning of expansion. In everyday experience, expansion implies growth into something else. A balloon inflates into the surrounding air, a puddle spreads across the ground. But in curved space, expansion is intrinsic. Galaxies do not fly outward into pre-existing void. Rather, the metric of space itself stretches, increasing the distances between them. A photon of a light, emitted billions of years ago, does not simply travel through space. It travels through a changing geometry, its wavelength stretched along the way. This cosmic redshift is not motion in the ordinary sense, but a fingerprint of expanding space-time. Mathematically, this is described by the Friedmann equations, derived from Einstein's general relativity. These equations link together the expansion rate, matter density, curvature, and energy of the universe. They form the backbone of modern cosmology, allowing scientists to model everything from the earliest instance of the Big Bang to the projected fate trillions of years into the future. Each observation, whether of galaxy clusters, microwave background ripples, or subtle oscillations in large-scale structure, feeds back into this framework, refining our picture of cosmic geometry. Perhaps most importantly, curved space reframes the question of whether the universe has an outside. If space is curved, it may be finite yet unbounded, much like the surface of a sphere. The two-dimensional surface of Earth does not require an external edge to exist. Its geometry is complete in itself. Likewise, our three-dimensional cosmos may be complete without needing a surrounding container. Expansion alters distances within this geometry, but it does not spread into anything beyond. To ask what lies outside space is to misunderstand its nature, much as asking what lies beyond the end of a circle misses the point that a circle has no end. Still, speculative theories propose that higher dimensions may exist. String theory, for example, suggests that space may contain additional dimensions curled up too tightly to observe. In some models, our universe is a three-dimensional brain floating within a higher dimensional bulk. Expansion, in this view, could be seen as motion within that larger framework. Such ideas, while fascinating, remain untested. For now, cosmology grounds itself in the three observable dimensions and the elegant geometry of general relativity. Curved space, then, is not a metaphor but a reality, an invisible architecture shaping the path of every photon and the fate of every galaxy. It explains why redshift occurs without motion through space, why galaxies recede without a center, and why the universe can be finite without an edge. Yet even as geometry defines the structure of the cosmos, our view of it remains bounded by another limit, the horizon of what we can observe. And so, after exploring the curvature of space itself, we arrive at a deeper question. What is the nature of this cosmic horizon, the ultimate boundary of our vision, the line beyond which lies a universe forever hidden from our reach? The observable horizon is one of the most fundamental boundaries in cosmology, yet it is not a physical wall or a tangible barrier. It is defined by a combination of cosmic factors, the finite age of the universe, the speed of light, and the ongoing expansion of space. Light travels at 299,792 kilometers per second, a constant in all frames of reference. The universe itself is roughly 13.8 billion years old, giving rise to an immediate intuition that we should be able to see objects no farther than 13.8 billion light-years away. However, this simple calculation does not account for a critical factor. Space has been expanding continuously while photons traverse it. As a result, the light we observe today has travelled through a universe that was smaller when the light began its journey, stretching across a growing distance as it moved. By modelling this expansion with the framework of general relativity, astronomers determined that the most distant galaxies detectable from Earth today are about 46 billion light-years away, even though their light was emitted nearly the full age of the universe ago. This distance is the radius of the observable universe, an immense sphere within which every photon has had time to reach us. This observable horizon is not fixed. As cosmic time advances, light from ever more distant sources gradually reaches our telescopes. New regions of the universe emerge into visibility, slowly revealing the structures and galaxies that formed in the early cosmos. Simultaneously, the expansion of space ensures that other regions move beyond detection. Because space itself stretches, there exist galaxies so distant that their recession velocity exceeds the speed of light relative to us. Photons emitted from these galaxies today will never arrive at Earth. In this sense, the observable horizon is a dynamic boundary. It both grows with time and simultaneously limits the regions that will remain perpetually beyond our reach. The most ancient light accessible to observation comes from the cosmic microwave background, CMB, the relic radiation emitted when the universe was only 380,000 years old. Before this epoch, the universe was a dense, opaque plasma in which photons scattered repeatedly off free electrons. Light could not travel freely. When electrons combined with protons to form neutral hydrogen, a process known as recombination, the universe became transparent, and photons began their unimpeded journey through space. These photons now reach us as the microwave background, forming an observational wall that marks the earliest light in the cosmos. To probe epochs earlier than this, scientists must rely on other cosmic messengers. Neutrinos, nearly massless particles that interact weakly with matter, decoupled from the primordial plasma mere seconds after the Big Bang. Gravitational waves, ripples in space-time itself, could carry information from the first fractions of a second of cosmic history, including signals from inflation. Experiments such as LIGO, Virgo, and planned space-based observatories aim to detect these faint echoes, potentially extending the observable horizon beyond the reach of photons. Understanding the observable horizon also emphasizes the critical distinction between the observable universe and the total universe. The observable region is limited by the combination of light speed and cosmic time, the portion of the cosmos from which information has had time to reach us. Beyond this horizon, space may continue indefinitely, perhaps containing countless galaxies and structures forever inaccessible. In fact, if the universe is infinite, no matter how long we wait, there will always exist regions beyond any observational limit. While we can measure and model the expansion of the observable universe, we cannot directly confirm the total extent of space, leaving open the possibility that the full cosmos dwarfs what we can see. Cosmologists extract enormous value from this horizon despite its limitations. Detailed observations of galaxies approaching the horizon reveal subtle patterns imprinted in the early universe. One such pattern is baryon acoustic oscillations, relics of sound waves rippling through the plasma before recombination. These oscillations left a characteristic scale in the distribution of matter, acting as a cosmic ruler that allows precise measurement of distances and the rate of expansion. Similarly, fluctuations in the cosmic microwave background encode information about the geometry, composition, and density of the universe. By analysing the CMB's temperature variations down to microkelvin precision, scientists can infer the proportions of ordinary matter, and dark energy, as well as the flatness of space on the larger scales. These observations confirm that the universe is expanding and that this expansion is accelerating, driven by the enigmatic force known as dark energy. The horizon also illuminates profound questions about causality and cosmic uniformity. Regions that now lie at opposite extremes of the observable universe were once close enough to interact physically in the earliest moments after the Big Bang. This connectivity explains the remarkable uniformity of the cosmic microwave background. Nearly identical temperatures are measured across regions that are now causally disconnected. Without an early mechanism such as inflation, it would be difficult to reconcile how distant patches of the sky could have equilibrated. Inflation posits a brief period of exponential expansion, stretching a once homogeneous region to immense scales. The observable horizon therefore preserves the imprint of processes that occurred long before galaxies formed, serving as a time capsule for the universe's infancy. Yet the observable horizon imposes a fundamental limitation. No matter how powerful our telescopes become, whether the Hubble Space Telescope, the James Webb Space Telescope, or successors yet to be built, there will always remain a realm beyond observation. We can approach the horizon ever more closely, capturing galaxies formed within a few 100 million years of the Big Bang. But the boundary itself ensures that a vast cosmic expanse will remain unseen. Even as we map the structure of the observable universe with exquisite precision, we must acknowledge that this is only a fraction of the total. The cosmic horizon is simultaneously a window and a wall. The presence of this horizon reframes the question of expansion in striking ways. If galaxies beyond 46 billion light-years are forever unreachable, are they still part of the universe? Cosmology answers yes. They exist within the same fabric of space, governed by the same physical laws, even if their light will never arrive. Expansion carries them apart faster than photons can traverse the distance. Yet this does not imply an edge. Rather, it demonstrates that the universe is unbounded in principle, and that distance itself grows with time. The observable horizon reminds us that human knowledge is inherently limited by physical laws, and that the portion of the cosmos accessible to measurement is only a fragment of a vastly larger whole. The horizon also provides context for one of the most mysterious aspects of modern cosmology: dark energy. The acceleration of expansion means that more and more galaxies are moving beyond the horizon every second. Dark energy dominates the dynamics of the universe on the larger scales, pushing galaxies apart and shaping the ultimate boundary of observation. In a sense, the horizon is not merely a passive limit, it is actively shaped by the energy content of space. The combination of finite light speed, ongoing expansion, and dark energy defines what we can see, what we will see, and what will remain forever beyond reach. In practical terms, the observable horizon gives cosmologists both constraints and opportunities. It defines the scale at which statistical measurements of galaxy distributions become meaningful. It provides a framework for comparing theoretical models with observable reality. And it offers insight into the early universe by encoding the history of expansion and the growth of structure. Every new discovery, every faint distant galaxy imaged, every tiny fluctuation measured in the cosmic microwave background extends the boundary of our knowledge, yet simultaneously underscores that some regions will always remain hidden. Ultimately, the observable horizon is a profound reminder of both limitation and context. It shows that while the universe is vast, structured, and measurable, human observation is bounded. Beyond 46 billion light-years, galaxies recede faster than their light can travel, dark energy ensures continued acceleration, and the totality of space may extend indefinitely. Within this finite observable sphere, however, we can reconstruct nearly 14 billion years of cosmic history, mapping the formation of galaxies, clusters, and superclusters, and tracing the imprints of the earliest moments of creation. Yet even as we explore this boundary, the horizon provokes deeper questions. If there are regions forever beyond sight, what does that mean for the nature of the universe itself, for the geometry of space, and for the ultimate fate of everything we can never hope to witness? The observable horizon, in both its presence and its limits, sets the stage for the next mystery that drives cosmology forward, the accelerating expansion governed by dark energy, and the challenge of understanding why space itself grows faster with time. Dark energy entered the scientific lexicon in the late 1990s, when astronomers observing distant Type Ia supernovae stumbled upon a discovery that would reshape modern cosmology. These stellar explosions, the cataclysmic end of white dwarf stars in binary systems, serve as remarkably reliable standard candles. Because their intrinsic brightness is consistent, astronomers can measure their apparent brightness and calculate precise distances, even across billions of light-years. Teams led independently by Saul Perlmutter, Brian Schmidt, and Adam Riess set out to track the expansion history of the universe by comparing the brightness of distant supernova to what would be expected if the universe was slowing under the influence of gravity. The assumption was straightforward. Matter's gravitational pull should decelerate the expansion, meaning distant supernova would appear brighter than predicted by a constant rate of expansion. The results were shocking. Instead of a universe slowing down, the data revealed that galaxies hosting these supernovae were receding faster than expected. The universe's expansion was not decelerating, it was accelerating. The implication was profound. Something pervasive and unseen was exerting a repulsive influence on the cosmos. The significance of this discovery earned the 2011 Nobel Prize in Physics for Perlmutter, Schmidt, and Riess, and it heralded a new era in cosmology. Observational techniques, refined over decades, had revealed a force acting on the larger scales, fundamentally altering the story of cosmic evolution. To describe this acceleration, scientists introduced the concept of dark energy, a form of energy that permeates space itself and exerts negative pressure. In Einstein's field equations of general relativity, pressure contributes to the gravitational dynamics of space-time just as mass and energy do. Ordinary matter produces attractive gravity, pulling objects together. Dark energy, by contrast, exerts a negative pressure, effectively producing a repulsive gravitational effect. This force drives galaxies apart, accelerating the expansion of the universe. Unlike gravity, which becomes weaker over distance, dark energy is thought to act uniformly across the cosmos, influencing every cubic meter of space equally, regardless of the distribution of matter. Current measurements suggest that dark energy accounts for approximately 68% of the total energy density of the universe. Dark matter contributes about 27%, while ordinary matter, the familiar atoms that compose stars, planets, and living organisms, accounts for less than 5%. These proportions highlight a striking reality. The universe we perceive through telescopes and direct observation is a minority of its content. Most of the cosmos is invisible, detectable only through its gravitational or expansive effects. Dark energy dominates the dynamics of the universe on the larger scales, yet its fundamental nature remains enigmatic, one of the most profound mysteries in contemporary physics. One possibility is that dark energy corresponds to the cosmological constant, a term Einstein introduced in 1917 in his equations to allow for a static universe. At that time, the prevailing belief was that the cosmos was eternal and unchanging, and the cosmological constant provided a counterbalance to gravity. Following Hubble's discovery of expansion in 1929, Einstein reportedly dismissed the term as his greatest blunder, recognizing that a dynamic universe rendered it unnecessary. Yet with the discovery of accelerated expansion, the cosmological constant regained relevance. In this interpretation, dark energy represents the energy inherent to empty space, a vacuum energy that remains constant as the universe expands. The problem lies in theoretical predictions. Quantum field theory estimates a vacuum energy density vastly larger than what is observed, by as much as 120 orders of magnitude, a discrepancy so extreme it is widely regarded as the most severe conflict between theory and observation in physics. Reconciling this gap remains an unresolved challenge. Alternative models suggest that dark energy may be dynamic, changing over time rather than remaining constant. Theories such as quintessence propose a slowly evolving field whose energy density varies, influencing the expansion rate differently at different epochs. A dynamic field could account for subtle anomalies in observational data that a constant cosmological constant cannot easily explain. Researchers test these models through precise measurements of distant supernovae, the large-scale distribution of galaxies, and the cosmic microwave background. However, as yet, there is no definitive observational evidence demonstrating time variation in dark energy's properties, leaving the constant cosmological interpretation as the simplest explanation. Some proposals go even further, challenging the fundamental assumptions of general relativity. Modified gravity theories attempt to account for accelerated expansion not through an additional energy component, but by altering the equations that describe gravity on cosmic scales. These theories posit that gravity itself may behave differently over immense distances, producing acceleration without invoking dark energy. While intriguing, such models struggle to reproduce the detailed structure observed in the cosmic microwave background and in galaxy surveys. Consequently, general relativity supplemented with dark energy remains the most consistent framework. The presence of dark energy profoundly shapes the future of the universe. If it is a cosmological constant, expansion will continue indefinitely. Galaxies will drift farther apart, star formation will cease, and the universe will gradually approach a cold, dilute state, a scenario known as heat death. If dark energy increases over time, it could eventually dominate all other forces, tearing apart galaxies, stars, planets, and even atomic nuclei in a hypothetical Big Rip. Conversely, if dark energy diminishes, gravity might regain control, potentially halting expansion or even reversing it in the distant future. Each scenario hinges on the precise nature of dark energy, a factor that remains experimentally elusive. Dark energy also challenges intuitive notions of space and nothingness. If expansion occurs not into pre-existing space, but as a stretching of geometry itself, dark energy can be interpreted as the driver of that evolving geometry. What humans once considered empty space, the vacuum between stars and galaxies, is in fact filled with energy that determines the universe's fate. Its effect is not localized, it operates uniformly across all of space. Observations suggest that the space between galaxies is dominated not by emptiness, but by the energy of dark energy, a force invisible yet overwhelmingly influential. Contemporary and forthcoming missions aim to probe dark energy with ever-increasing precision. The Dark Energy Survey maps hundreds of millions of galaxies, tracking cosmic structure over billions of light-years. The European Space Agency's Euclid mission and NASA's Roman Space Telescope are designed to measure the subtle bending of light caused by gravitational lensing and to catalogue supernovae across cosmic time. These projects aim to determine whether dark energy is truly constant or varies dynamically, and whether modifications to gravity might be necessary. Each data point contributes to understanding the expansion history of the universe, refining cosmological models and constraining theoretical possibilities. Even with these efforts, the fundamental question remains unresolved. Dark energy is measurable with precision, yet conceptually elusive. It forces a re-evaluation of what empty space means, of how expansion operates, and of the broader structure of the cosmos. It confronts humanity with a universe whose vast majority is invisible, whose growth defies ordinary intuition, and whose destiny is dominated by a phenomenon that cannot be directly touched or seen. Some theorists speculate even further. Could the acceleration of expansion be a hint of realities beyond our universe? Models of the multiverse propose that our observable cosmos is only one of countless universes, each with its own physical laws. In such scenarios, dark energy might reflect interactions between these universes or indicate that the geometry of space is part of a larger, higher dimensional framework. While these ideas remain speculative, they highlight how the discovery of dark energy has expanded the conceptual horizon of cosmology, forcing physicists to confront questions that are at once observable and almost unfathomable. Dark energy, therefore, is both a measurement and a mystery. It is quantifiable in its effects on cosmic expansion, yet opaque in its fundamental nature. It dominates the cosmos, governs its ultimate trajectory, and reshapes our understanding of space, emptiness, and the structure of reality itself. And as we seek to measure, map, and model it with ever greater precision, the presence of dark energy points inevitably toward the deeper question that has motivated cosmologists for decades. If the universe is expanding, driven by a force we cannot see, what does this reveal about the fabric of reality, the dimensions of space, and what, if anything, lies beyond everything we can ever observe? The multiverse hypothesis emerges from the recognition that our universe's expansion, its large-scale geometry, and even the fundamental laws that govern it may not be unique. The notion is not introduced as mere speculation or science fiction. It arises naturally from established cosmological models, particularly those connected to inflationary theory. Inflation proposes that the universe underwent an extraordinary period of exponential expansion in the first fraction of a second after the Big Bang, stretching space by a factor of at least 10 to the 26th power in a time span shorter than a trillionth of a second. The evidence for this process comes from precise measurements of the cosmic microwave background, which reveal remarkable uniformity punctuated by tiny fluctuations. Yet inflation also predicts more than uniformity. Under certain conditions, it suggests that inflation may not have ended everywhere simultaneously. In some regions, the rapid expansion ceased, giving rise to localized universes like ours. In others, inflation continued, creating new regions with different physical properties. This process, known as eternal inflation, leads naturally to the idea of a multiverse, a vast and possibly infinite landscape of universes, each a separate bubble embedded within the inflationary medium. In this context, the long-standing question of what the universe expands into acquires a new layer of complexity. Each bubble universe expands within its own self-contained space. There is no single external void into which all universes expand. Instead, expansion occurs in the geometries defined locally by the energy driving inflation. In principle, collisions between these universes could leave observable imprints. Some researchers have speculated that unusual cold or hot spots in the cosmic microwave background, such as the CMB cold spot, might be remnants of past collisions with neighbouring universes. However, these observations remain inconclusive, and no definitive evidence has yet emerged to confirm inter-universal interaction. Nevertheless, the mathematical framework of eternal inflation renders the multiverse plausible, even if direct observation may forever remain out of reach. The multiverse concept also finds support in string theory, a leading candidate for a unified description of all fundamental forces and particles. String theory predicts a vast landscape of possible vacuum states, each corresponding to a different configuration of extra dimensions, physical constants, and particle properties. In this landscape, our universe is just one realization among an astronomical number of possibilities. The fine-tuning of fundamental constants, the strength of gravity, the cosmological constant, or the masses of elementary particles appears astonishingly precise. Slight deviations would render the formation of galaxies, stars, or even complex chemistry impossible. In a multiverse, however, this apparent fine-tuning is no longer surprising. Among countless universes, it is inevitable that some will possess conditions compatible with life, and we exist in one such universe simply because only these conditions allow observers to emerge. This perspective reframes questions about necessity versus contingency, suggesting that many features of our universe are local outcomes rather than universal absolutes. Yet the multiverse hypothesis faces profound conceptual and practical challenges. By definition, regions beyond our observable horizon are inaccessible to measurement. Critics argue that this places the idea outside the domain of empirical science. Without testable predictions, how can it be evaluated? Proponents counter that the multiverse is not a speculative add-on, but a consequence of models that are themselves supported by observation, such as inflationary cosmology and string theory. If the underlying models predict multiverse behavior as a natural outcome, then the multiverse can be considered a legitimate inference, albeit one that may remain forever beyond direct verification. Within this framework, the nature of expansion is profoundly non-intuitive. Bubble universes do not expand into a pre-existing void. Each expands within its own intrinsic geometry. The outside is not a shared space, but the continuation of inflationary fields that generate new regions. Expansion, therefore, is not outward motion into an external container, but the evolution of geometry and energy conditions intrinsic to the cosmos. The universe we inhabit is not the center of all expansion. It is simply one region where inflation has ended, embedded in a larger multiversal structure that may continue indefinitely. From this perspective, the question, what is the universe expanding into, becomes less about space beyond and more about the process that generates universes. The expansion is an emergent property of the energy fields driving inflation, and the boundary we perceive is defined not by a physical edge, but by causal and temporal limits. Philosophical implications follow naturally from this view. If the multiverse exists, our universe is neither unique nor central. Every conceivable configuration of matter and energy may exist somewhere. Laws of physics, which we consider fundamental, might be local rules applying only within our bubble, while other regions obey different principles. The multiverse challenges traditional notions of ultimate explanation, suggesting that some features of reality may be contingent rather than necessary, a product of cosmic chance rather than universal law. Questions about the uniqueness of constants, the inevitability of cosmic history, and the origins of life take on a different character. We inhabit a universe that permits our existence, but countless other universes could exist with conditions utterly alien to what we observe. Some researchers have sought indirect signatures of the multiverse, statistical anomalies in the cosmic microwave background, unexplained alignments of fluctuations or unexpected voids in galaxy distributions could hint at influences from regions beyond our observable universe. A subtle anisotropy might be interpreted as a gravitational influence from a neighbouring universe, or as a vestige of an ancient bubble collision. So far, no signal has reached statistical significance sufficient to confirm these hypotheses, yet future missions with improved sensitivity and broader sky coverage may probe these possibilities in greater detail. Instruments capable of mapping the universe across vast scales, detecting subtle lensing effects, or measuring polarization patterns in the CMB could provide indirect evidence that informs multiverse models. Whether or not the multiverse exists, its consideration expands the framework of cosmological thinking. Traditional questions about edges, boundaries, and external space give way to inquiries about the generation of universes, the dynamics of inflation, and the interplay of geometry and energy at scales beyond direct observation. Expansion, in this view, is a feature not only of our own universe but of potentially countless others, each with its own horizon, history, and fate. The multiverse encourages us to reinterpret what it means for space to stretch, for light to travel, and for physical laws to operate. Yet while the multiverse remains speculative, it is connected to other avenues of inquiry into the nature of expansion. One of the most compelling involves extra dimensions, a concept with firm mathematical grounding in string theory and other advanced frameworks. If the three spatial dimensions we observe are embedded within a higher dimensional structure, cosmic expansion might involve motion, or stretching, not just in familiar space but within a broader multidimensional geometry. These dimensions, if compactified or otherwise hidden, could influence the expansion rate, the behavior of gravity, and the formation of large-scale structure. They offer a complementary perspective to the multiverse, suggesting that what appears infinite or unbounded in 3 dimensions might have deeper organization in higher dimensional space. The multiverse, therefore, serves both as a theoretical extension of inflation and as a lens through which to interpret dark energy, geometry, and expansion. It challenges intuitive notions of space and edge, redefining expansion as an emergent feature of underlying physics rather than a motion into nothingness. It suggests that the cosmos we observe is just one of many possible realities, and that our laws, constants, and cosmic history may be local phenomena within a broader, potentially infinite ensemble. and while empirical confirmation remains elusive, the multiverse provides a conceptual bridge linking observed expansion, dark energy, inflation, and the profound mysteries of what lies beyond the observable universe. The idea of extra dimensions arises from the recognition that the universe we perceive, 3 spatial dimensions and 1 temporal dimension, may be only a limited projection of a far more intricate reality. In daily life, we navigate a world of length, width, height, and the inexorable passage of time. Yet the forces that govern matter, energy, and the cosmos suggest a deeper structure. Attempts to unify gravity with electromagnetism, and later all fundamental forces, have consistently pointed toward the existence of additional spatial dimensions, hidden from ordinary perception, either by extreme compactification or by their exotic nature. These dimensions, while invisible, may be essential for understanding why the universe expands, why its constants take the values they do, and even what it truly means for expansion to occur without an external void. The seeds of this idea were planted nearly a century ago. In the 1920s, Theodore Kaluza proposed an audacious extension of Einstein's general relativity, adding a 5th dimension to space. Kaluza noticed that by introducing this extra dimension and imposing periodicity, essentially curling it up so tightly that it remained undetectable, one could naturally derive Maxwell's equations of electromagnetism alongside Einstein's equations of gravity. Shortly afterward, Oscar Klein suggested that this extra dimension might be compactified at a scale so small as to be unobservable, giving rise to the so-called Kaluza-Klein theory. While initially a mathematical curiosity, this framework set the stage for more sophisticated models in the latter half of the 20th century, particularly as physicists sought a unified theory encompassing all forces. The emergence of string theory in the 1970s and 1980s provided both motivation and necessity for extra dimensions. In string theory, the fundamental constituents of matter are not point-like particles, but tiny vibrating strings, whose modes of vibration determine particle properties such as mass and charge. For the mathematics to be internally consistent, the theory requires not 4 but 10 or 11 dimensions, depending on the specific formulation. These additional dimensions are compactified into complex geometries known as Calabi-Yau manifolds, with shapes so intricate that they could influence particle interactions, the strengths of forces, and perhaps even the behavior of cosmic expansion. While no experiment to date has directly detected these dimensions, their existence could provide answers to persistent puzzles. Why gravity is so weak compared with other forces, why elementary particles have the masses they do, and why the universe's expansion unfolds according to the patterns we observe. Some modern theories propose that our visible universe resides on a 3-dimensional brane, floating in a higher dimensional space, referred to as the bulk. In this scenario, all familiar matter and electromagnetic forces are confined to the brane, while gravity can leak into the higher dimensional bulk. The expansion of the universe could then be interpreted as the stretching of the brane itself, rather than motion into an external void. Interactions between branes or collisions within the bulk could potentially trigger events resembling a Big Bang, giving birth to new universes with varying physical properties. Within this framework, the concept of outside is redefined. Expansion does not require an empty void surrounding the universe. Instead, it occurs intrinsically within a multi-dimensional structure that hosts branes, energy fields, and potentially multiple universes. Experimental investigation of extra dimensions remains challenging but not impossible. Particle accelerators such as the Large Hadron Collider, LHC, search for evidence through high-energy collisions that might reveal signatures of hidden dimensions. Hypothetically, extra dimensions could manifest as missing energy or momentum, or even in the creation of miniature black holes, phenomena that would otherwise be inexplicable in standard 4-dimensional physics. So far, no definitive evidence has been found, but the experiments have constrained the possible size and properties of extra dimensions, placing upper limits on their scales down to fractions of a millimeter. On cosmological scales, gravity itself may offer clues. If gravitational forces can leak into higher dimensions, their influence on galaxy clustering, cosmic microwave background patterns, or gravitational waves could differ subtly from predictions based solely on 4-dimensional general relativity. Precision measurements of large-scale structure and gravitational lensing thus provide indirect but increasingly powerful tools for probing hidden dimensions. The existence of extra dimensions also offers a novel perspective on the universe's accelerated expansion. Some models suggest that what we interpret as dark energy, the mysterious force driving galaxies apart, is in fact an emergent effect of higher dimensional geometry. In such scenarios, the bulk may exert influence on the brain, producing an apparent negative pressure that mimics the cosmological constant. If true, the acceleration of cosmic expansion would not arise from a substance filling space, but from the dynamics of dimensions beyond our perception. This possibility bridges two of the most profound mysteries in cosmology: dark energy and the hidden structure of space itself. Thinking in terms of extra dimensions fundamentally changes how we conceptualize cosmic expansion. In familiar three-dimensional space, expansion is often visualized as galaxies moving apart into empty space, like dots on the surface of an inflating balloon. Yet in a higher dimensional framework, this intuition fails. Expansion may be analogous to the projection of a higher dimensional object into three dimensions. What appears to be simple stretching is actually the result of complex multi-dimensional dynamics. Asking what the universe expands into is therefore akin to asking what a shadow expands into when the object casting it moves. The true action occurs in dimensions invisible to the observer. Theoretical models also suggest that extra dimensions may help unify diverse aspects of physics, linking gravity, quantum mechanics, and cosmology. Compactified dimensions can determine the values of coupling constants, influence symmetry, breaking in particle physics, and even affect the large-scale structure of the cosmos. In some scenarios, fluctuations in these hidden dimensions could leave subtle imprints on the cosmic microwave background or the distribution of galaxies, providing indirect evidence of their presence. Observational cosmology, combined with high-energy physics, thus offers a promising route toward testing these ideas, even if direct detection of extra dimensions remains beyond current technology. Despite the elegance of these models, the challenge of experimental confirmation is immense. The scales involved may be far smaller or far larger than what human instruments can probe, and the effects may be subtle, requiring extraordinary precision to detect. Yet the pursuit of evidence drives innovation. Gravitational wave observatories, next-generation particle colliders, and ultra-sensitive telescopes all contribute pieces to the puzzle. Each measurement refines constraints, guiding theorists toward models consistent with both mathematics and observation. Ultimately, extra dimensions redefine the very meaning of the universe's expansion. Space is not merely stretching into nothing. Its geometry may be embedded in a higher dimensional framework that shapes the dynamics we observe. Dark energy, the cosmic microwave background, galaxy clustering, and gravitational interactions may all reflect this deeper structure. In this sense, the universe is far richer than our senses reveal, with layers of geometry and energy hidden from direct view, but shaping every observable phenomenon. While the evidence remains circumstantial, the theoretical implications are profound. Expansion, geometry, and even the origin of the cosmos may be inseparable from the unseen dimensions that underlie reality. Extra dimensions also emphasize the interplay between the observable and the theoretical. While telescopes and detectors reveal the visible universe, mathematical models extend our vision into realms beyond perception, suggesting that our three-dimensional experience is only part of a larger, multi-dimensional tapestry. The stretching of space, the movement of galaxies, and the acceleration driven by dark energy may all be projections of higher dimensional dynamics. Understanding these dimensions may ultimately answer not only why the universe expands, but also what the very notion of space means, a question that challenges intuition, observation, and the limits of human imagination. Thus, the idea of extra dimensions transforms cosmology from a study of the universe as a three-dimensional expanse into an exploration of geometry, energy, and expansion in higher dimensional reality. It offers a framework in which the universe's growth, acceleration, and structure can be understood as intrinsic features of a multidimensional cosmos, rather than as motion into an external void. While empirical confirmation remains pending, the concept of extra dimensions continues to guide theoretical research, shaping the questions we ask about the origin, evolution, and ultimate fate of the universe. Mathematical models of the universe are the backbone of modern cosmology, providing a framework to understand the cosmos from its earliest moments to its ultimate fate. At the heart of these models lie Einstein's field equations of general relativity, formulated in 1915. These equations describe how matter and energy influence the curvature of spacetime, and conversely, how spacetime governs the motion of matter. In their full form, the equations are a set of 10 interrelated nonlinear partial differential equations, remarkably elegant but notoriously difficult to solve in general cases. To make progress, cosmologists adopt a crucial simplifying assumption: the cosmological principle, which asserts that the universe is homogeneous and isotropic on large scales. Homogeneity means that, on average, matter is distributed roughly evenly throughout space, while isotropy means the universe looks the same in all directions. These assumptions are supported by observations including the uniformity of the cosmic microwave background, CMB, and large-scale galaxy surveys. Applying these principles reduces the complexity of Einstein's equations, leading to a form suitable for modelling the evolution of the universe. The Friedmann equations, derived by Alexander Friedmann in the early 1920s. The Friedmann equations describe how the scale factor of the universe, a dimensionless quantity representing relative cosmic size, changes over time. By convention, the scale factor is set to 1 in the present epoch. Smaller values correspond to earlier times in the universe. The equations incorporate the energy content of the universe, including ordinary matter, radiation, dark matter, dark energy, and the curvature of space. They predict how the scale factor evolves under different conditions. For example, in a universe dominated by matter, expansion decelerates over time because the gravitational pull of matter slows the stretching of space. Conversely, in a universe dominated by dark energy, expansion accelerates, causing galaxies to drift apart at an ever-increasing rate. From these foundational equations, cosmologists have built the lambda-CDM model, or lambda-cold dark matter model, which serves as the standard framework of modern cosmology. This model includes the cosmological constant, lambda, representing dark energy, cold dark matter, a pressureless form of matter that clumps gravitationally, and ordinary baryonic matter, which makes up stars, planets, and interstellar gas. Observational evidence overwhelmingly supports lambda-CDM. Measurements of the CMB, galaxy redshift surveys, baryon acoustic oscillations, and gravitational lensing all align with the predictions of the model. According to lambda-CDM, the universe is approximately 13.8 billion years old, remarkably flat on large scales, and composed predominantly of dark components. Around 68% dark energy, 27% dark matter, and just under 5% ordinary matter. One of the strengths of mathematical models lies in their predictive power. By integrating the Friedmann equations backward in time, cosmologists can reconstruct conditions in the early universe with astonishing precision. For instance, Big Bang nucleosynthesis, the formation of light elements in the first few minutes after the Big Bang, is predicted accurately using the observed baryon density. The predicted abundances of hydrogen, helium, and trace lithium match measurements from interstellar gas clouds and the oldest stars, providing compelling confirmation of the theory. Similarly, small density fluctuations in the early universe, imprinted in the cosmic microwave background, grow over billions of years into the intricate web of galaxies, clusters, and filaments we observe today. The alignment of theory and observation across these disparate phenomena is a testament to the robustness of the models, yet these models also illuminate deep unresolved puzzles. One of the most striking is the discrepancy between the predicted and observed vacuum energy. Quantum field theory suggests that even empty space should possess an enormous energy density due to fluctuations in quantum fields. When plugged into Einstein's equations, this energy density predicts a cosmological constant up to 120 orders of magnitude larger than what we observe. This is perhaps the largest mismatch between theory and observation in the history of physics, highlighting a fundamental gap in our understanding. Similarly, while the Friedmann equations predict the gravitational effects of dark matter, they do not reveal its nature. What particle or entity constitutes dark matter remains unknown, despite its dominant role in shaping cosmic structure. Mathematical models also allow cosmologists to explore the fate of the universe. By solving the Friedmann equations with varying parameters, different scenarios emerge. In a matter-dominated universe, expansion might eventually slow and reverse, culminating in a big crunch where all matter collapses back into a dense state. In a dark, energy-dominated universe, expansion accelerates indefinitely, leading to a cold, dilute cosmos as galaxies recede beyond one another's observable horizons. Variations in the equation of state of dark energy, the ratio of pressure to energy density, determine whether the universe experiences a gentle heat death, a catastrophic big rip, or a more nuanced transformation. Each scenario flows naturally from the same mathematical framework, illustrating the predictive flexibility of these models. Crucially, the equations clarify why the universe's expansion does not require an outside. The scale factor does not measure growth into an external void. It quantifies changes in distances between points within space itself. In other words, space stretches, carrying galaxies along with it, without expanding into a pre-existing arena. This can be compared to the circumference of a circle. One can define and measure it entirely within the two-dimensional plane of the circle, without invoking a surrounding three-dimensional space. Similarly, the universe's expansion is fully described by the internal geometry and energy content of spacetime. The Friedmann equations handle the evolution of curvature, density, and expansion in a self-contained manner, making the concept of an external outside unnecessary. Despite their elegance, the models are not immutable truths. They depend on parameters measured through observation, and new data can reveal tensions or anomalies. A prominent example is the Hubble tension, the discrepancy between measurements of the Hubble constant derived from the early universe using CMB data and those derived from the local universe using Cepheid variables and type Ia supernovae. The early universe measurements suggest a slower expansion rate, while local observations imply a faster one. This mismatch could point to systematic errors in observations or, tantalizingly, to new physics beyond lambda CDM, such as interactions in the dark sector or modifications to general relativity. Either way, the tension underscores that mathematical models are evolving tools, refined as observations become ever more precise. One of the remarkable features of these models is their balance of simplicity and depth. A handful of equations capture the evolution of a universe containing billions of galaxies, intricate large-scale structures, and complex cosmic histories. Within this mathematical framework lie the keys to expansion, structure formation, and ultimate fate. Observations, from the faint afterglow of the Big Bang to the motions of distant galaxies, converge on these models, validating their predictive power while leaving room for profound mysteries. To communicate these abstract ideas to a broader audience, cosmologists often rely on analogies, the most familiar of which is the balloon analogy. Here, galaxies are imagined as dots on the surface of an inflating balloon. As the balloon expands, the dots move away from one another, yet none is moving through the surface itself. The expansion occurs in the surface's geometry. While this analogy is imperfect, limited to 2 spatial dimensions rather than 3, it captures the essence of expansion in a self-contained space. The scale factor in the Friedmann equations formalizes this intuitive picture, allowing precise calculation of distances, velocities, and the age of the universe, rather than relying solely on metaphor. Mathematical models thus provide both quantitative rigor and conceptual clarity. They bridge observation and theory, offering predictions that can be tested against measurements, while simultaneously reshaping our understanding of space, time, and expansion. Yet they also point to profound mysteries: the nature of dark energy and dark matter, the origins of vacuum energy, and the ultimate fate of the cosmos. These are questions not just of astronomy or physics, but of fundamental reality itself. As observational capabilities improve, through new space telescopes, gravitational wave detectors, and high-energy particle experiments, the models will continue to evolve, incorporating fresh data and pushing the boundaries of understanding. In essence, mathematical models of the universe are more than equations. They are a lens through which we perceive the cosmos. They define expansion internally, describe the distribution and evolution of matter and energy, and guide inquiry into the unknown. They allow us to see the universe not as a static backdrop, but as a dynamic, evolving entity governed by precise laws. And while they answer many questions, they also invite deeper inquiry, challenging us to reconcile human intuition with the profound, sometimes counterintuitive reality of a universe without edges, yet rich in structure and mystery. The balloon analogy is one of the most widely used tools for illustrating the nature of cosmic expansion, yet it requires careful handling to avoid misconceptions. At its core, the analogy seeks to convey a truth that is both profound and counterintuitive. The universe is not expanding into a pre-existing void, and there is no central point from which everything is moving away. In this analogy, the surface of an inflating balloon represents the fabric of the universe. As air is added to the balloon, its surface stretches, and any points drawn on it representing galaxies move away from one another. No single point occupies a privileged position. Every point sees all others receding. This illustrates a central principle of cosmology. Galaxies are not travelling through space from a central explosion, but rather it is the fabric of space itself that expands, increasing the distances between all points over time. One of the most immediate strengths of the balloon analogy is its accessibility. It provides an intuitive way to understand why the universe does not have an edge, at least in the observable sense. Just as a two-dimensional being living on the surface of a balloon would perceive no boundary, our three-dimensional universe requires no physical edge. Expansion is intrinsic, a property of the space itself, rather than a process occurring within an external environment. The analogy also elegantly explains why galaxies appear to recede faster the farther away they are. On the balloon, 2 points located on opposite ends of the surface will separate more rapidly as the balloon inflates, simply because the distance along the surface is stretching. In the same way, the velocity at which distant galaxies recede is proportional to their distance from an observer, consistent with Hubble's law. Yet despite its utility, the analogy has significant limitations. The balloon expands into the surrounding air, giving the impression that an external space is required for expansion to occur. In contrast, the universe does not need anything outside of itself. General relativity describes cosmic expansion as a stretching of space-time itself, and this description does not invoke an embedding space. The analogy can inadvertently lead to the misconception that our three-dimensional universe is inflating into a higher dimensional void, which is not necessary according to current physics. Additionally, the balloon surface is a two-dimensional sphere, which might imply a finite, closed universe. Observations, however, suggest that the universe is flat on the larger scales, with geometry that may extend infinitely, a fact the balloon analogy cannot fully capture. Even with these caveats, the balloon analogy remains valuable when used carefully. It highlights the uniformity of expansion. Each observer, regardless of location, sees distant galaxies receding in a consistent manner. This universality underscores a profound truth. The universe has no center. Every point behaves as though it is the origin of expansion, a direct consequence of the geometry of space rather than the dynamics of individual galaxies. The analogy also conveys why photons from distant galaxies are redshifted. As space stretches, so too does the wavelength of light travelling through it. This cosmological redshift is not caused by motion through space, as with Doppler shifts in everyday experience, but by the stretching of space itself, a subtle but critical distinction. To refine the analogy further, educators often stress that galaxies are not like ink smeared across the balloon's surface. Instead, they are more akin to coins glued to the surface. The coins themselves do not stretch, but the distances between them increase as the balloon inflates. This distinction captures a key feature of cosmic expansion. Local structures, such as galaxies or galaxy clusters, are gravitationally bound and resist the stretching of space within them. Expansion dominates only on the vast scales between clusters and superclusters, emphasizing the difference between local and global dynamics. Within the Milky Way, for example, gravity holds stars in orbit and prevents the galaxy itself from expanding. Yet across millions of light years, space stretches and galaxies drift apart. The balloon analogy also sheds light on the observable horizon. Just as a creature confined to the surface of the balloon cannot see beyond the curvature of its world, we cannot see beyond the limits set by the speed of light and the finite age of the universe. Light from galaxies beyond a certain distance has not had time to reach us, defining a cosmic horizon that is not a physical barrier, but a boundary of visibility. In this context, any notion of an outside becomes irrelevant. A two-dimensional being on a balloon cannot interact with the air surrounding the balloon, and similarly, our universe's expansion is fully described within its own geometry, without reference to an external space. Despite its explanatory power, cosmologists caution that analogies are only entry points into complex concepts. The balloon analogy can guide intuition, but cannot replace the precise mathematics of general relativity and observational data. Misapplied, it risks reinforcing misconceptions, such as the idea of a universal center or an external void, rather than clarifying the nature of expansion. To fully understand cosmic dynamics, one must turn to Friedmann equations, Hubble's law, and detailed observations of the cosmic microwave background, galaxy distributions, and large-scale structure. Nevertheless, the balloon analogy provides a bridge between intuition and formal theory. It helps explain why galaxies beyond a certain distance can recede faster than the speed of light without violating relativity. Because it is the fabric of space itself that expands, there is no local motion faster than light. The galaxies are effectively carried along by the stretching of space-time. It also conveys the idea that expansion has been ongoing for 13.8 billion years, originating from a hot, dense early universe, but not from a single spatial point. Each galaxy, no matter where it is located, participates in this global expansion. The analogy can be extended to include different cosmological geometries. If the balloon represents a closed universe, travelling far enough in one direction might eventually return you to your starting point, just as circumnavigating the globe returns a traveller to the same city. If the universe is flat or open, the analogy shifts to depict an inflating rubber sheet or a saddle-like surface, emphasizing the stretching nature of space without implying a finite edge. This flexibility makes the balloon analogy a versatile educational tool when paired with careful clarification of its limitations. Ultimately, the balloon analogy illustrates a deeper philosophical point. The universe is self-contained. The question of what lies outside is fundamentally different from everyday experience. In ordinary life, objects exist within a larger context, but the universe itself encompasses all of space and time. Expansion is an intrinsic property of space-time, not a movement into something beyond. The analogy provides a tangible way to approach this abstract reality, showing how distances increase, how horizons form, and how no observer occupies a privileged position. Despite its simplicity, the analogy leads naturally to more rigorous exploration. Observations of the universe reveal that its geometry is remarkably flat on the larger scales, and its expansion is accelerating due to dark energy. The balloon metaphor helps visualize these phenomena, but cannot fully encapsulate them. The true description of cosmic expansion combines analogy, observation, and the mathematical framework of general relativity, creating a coherent picture of a universe that is both expanding and without boundary, mysterious yet measurable, infinite yet structured. Through careful explanation, the balloon analogy remains one of the most powerful tools for communicating the nature of cosmic expansion. It captures the counterintuitive idea that the universe has no center and no edge, clarifies the meaning of redshift, distinguishes local from global effects, and frames the concept of observable horizons. At the same time, it reminds us of the limits of intuition when confronting the vastness of the cosmos. Analogies guide the mind toward understanding, but the ultimate clarity comes from observation, mathematics, and the rigorous framework of cosmological models. Observations of the universe consistently point to an astonishing fact. On the largest scales, space is flat. This conclusion does not refer to flatness in the everyday sense, such as a tabletop or a calm horizon, but to the very geometry of spacetime itself. In practical terms, a flat universe means that parallel lines never converge or diverge, and the familiar rules of Euclidean geometry, triangles adding up to 180 degrees, the Pythagorean theorem holding true, apply even across billions of light years. This is a profound insight because it tells us that the universe, when considered at the grandest scales, behaves according to a simple, consistent order, rather than being warped or bent in unexpected ways. Yet this conclusion is not assumed. It is measured with precision, using the earliest light in the cosmos, the cosmic microwave background, as a primary diagnostic tool. The Planck satellite launched by the European Space Agency in 2009 provided the most detailed map of this ancient radiation to date. The cosmic microwave background, or CMB, is a relic from a time when the universe was merely 380,000 years old, a glowing fingerprint of the hot plasma that filled the cosmos shortly after the Big Bang. Within this radiation are tiny fluctuations in temperature and density, subtle variations of 1 part in 100,000, which encode a wealth of information about the universe's geometry. If the universe were positively curved, like the surface of a sphere, the fluctuations would appear larger on the sky than expected. Conversely, if the universe were negatively curved like a saddle, they would appear smaller. By analysing these fluctuations with exquisite detail, scientists found that the universe is flat to within 0.4%, a remarkable precision that speaks to the uniformity and simplicity of the cosmos on its grandest scales. Flatness has far-reaching implications. It tells us that the total energy density of the universe is extremely close to the critical density, the precise balance between a universe that would eventually collapse under its own gravity and one that would expand forever. Ordinary matter, the kind that makes up stars, planets, and people, is insufficient to reach this balance. To account for flatness, cosmologists must include dark matter and dark energy, unseen components that dominate the universe's energy budget. Together, these elements bring the total density to the critical value required for a flat cosmos. In this way, flatness not only informs us about geometry, but also about composition, revealing that the universe is largely invisible to our eyes and instruments, yet measurable through its gravitational and expansive effects. The near-perfect flatness observed today also provides powerful support for inflationary theory. Without inflation, any initial curvature present at the birth of the universe would have been magnified over time, making it improbable that we would observe such a flat cosmos billions of years later. Inflation proposes that in the first tiny fraction of a second after the Big Bang, the universe underwent an exponential expansion, stretching space so rapidly that any initial irregularities were smoothed away. This process would naturally drive the universe toward flatness, leaving the geometry we measure today. The observation of flatness thus serves as one of the strongest confirmations of inflation, linking the cosmos we see now with events that occurred in the universe's first infinitesimal moments. Yet the observation of flatness raises profound questions about the nature of space itself. If the universe is flat, does this imply that it is infinite? In principle, flat geometry could extend endlessly in every direction, without boundary or edge. This possibility suggests that the observable universe, vast as it is, may be only a tiny portion of a much larger whole, with galaxies and structures stretching beyond our detection forever. On the other hand, a flat universe can still be finite depending on its topology. Just as a video game can loop endlessly on a flat grid, connecting back on itself in ways not apparent from any local perspective, space could connect in a manner that allows a finite volume without any boundary. These scenarios challenge our intuition, inviting us to consider cosmic scales far beyond human experience, where the familiar notion of edges and limits may not apply. Flatness also influences the ultimate fate of the universe. In a closed, positively curved cosmos, gravitational attraction might eventually overcome expansion, leading to a reversal and a potential big crunch. In an open, negatively curved universe, expansion would continue indefinitely, though the geometric rules would differ from what we observe. With flatness, the future is less dictated by curvature and more by dark energy, the mysterious force driving the accelerating expansion of space. If dark energy remains constant, the universe will expand forever, becoming colder and more diffuse over unimaginable timescales. If dark energy evolves or varies, the future could be stranger still, from gentle slowing to scenarios such as the Big Rip, where all structures, from galaxies to atoms, are torn apart. Flatness sets the cosmic stage, but the behavior of dark energy directs the unfolding drama. Even in a flat universe, local curvature is abundant. Massive objects, galaxies, clusters, and black holes warp space-time around them, producing measurable effects such as gravitational lensing, where light from distant sources bends around massive foreground objects. These distortions provide a striking visual confirmation of general relativity and allow astronomers to map unseen matter, particularly dark matter. Yet when averaged over billions of light-years, these local curvatures cancel out, leaving a universe that is flat on the larger scales. This duality, local complexity embedded in a globally simple geometry, speaks to the remarkable consistency and elegance of cosmic structure. Flatness also clarifies why, The concept of an outside is unnecessary. If space extends infinitely in all directions, there is no edge to press against, no container into which it expands. Expansion occurs as distances between points within the universe increase, but there is no boundary at which expansion stops. Even in a finite yet unbounded topology, the universe remains self-contained, its geometry complete without reference to an external dimension. Flatness reinforces the insight that expansion is an intrinsic property of spacetime itself, not motion into a pre-existing void. Nonetheless, flatness does not eliminate the human urge to ponder boundaries. If the universe is infinite, what does that mean in physical terms? Can infinity be grasped conceptually, or does it remain an abstraction? If it is finite but unbounded, how can we visualize such a structure? These questions occupy the borderland between observation and philosophy, where science confronts the limits of intuition. Flatness pushes us to reconsider space not as a stage on which events occur, but as the very fabric within which events are embedded. A fabric without an edge, yet rich in structure, stretching, and history. Observational cosmology continues to probe flatness with ever greater precision. Measurements of the CMB, large-scale galaxy surveys, and patterns of gravitational lensing all converge on a universe that is extraordinarily flat, confirming the predictions of inflationary theory and constraining models of dark energy. Each new observation reinforces the picture of a cosmos that is both vast and uniform, yet dynamic, its expansion governed by the invisible forces of dark matter and dark energy. Flatness, in this sense, becomes a window into the fundamental workings of reality, linking geometry, energy, and cosmic history in a single, elegant framework. In the end, the flatness of the universe is more than a geometric property. It is a guide to understanding the cosmos itself. It informs our theories of the Big Bang, of inflation, of cosmic expansion, and of ultimate fate. It reshapes our intuition about space, boundaries, and infinity. And it invites us to contemplate a universe that is vast beyond comprehension, stretching without edge, yet governed by principles that can be measured, understood, and modelled. Flatness, precise and pervasive, is both a triumph of observation and a doorway to deeper mysteries, reminding us that the universe, though immense and seemingly infinite, follows rules that are discernible and consistent, waiting to be explored. When people ask whether the universe has an edge, they often imagine a physical boundary, a tangible limit comparable to the wall of a room, the rim of a container, or the edge of a cliff. Such imagery is natural because in everyday life, almost everything we interact with has a boundary. Tables have edges, oceans have shores, and planets have surfaces. Yet in cosmology, the concept of a boundary is far subtler, more abstract and profoundly counterintuitive. The universe, as we understand it, does not possess an edge in the conventional sense. Instead, what it has is a horizon, a limit set by the speed of light and the finite age of the cosmos. This horizon, sometimes called the observable universe, is defined by the distance light has travelled since the Big Bang, roughly 13.8 billion years ago. When corrected for the continuous expansion of space, this distance amounts to about 46 billion light-years in every direction. Beyond this observable horizon, there may be regions teeming with galaxies, clusters, and other structures, but we cannot see them. The light from these distant domains has not had enough time to reach us, and due to the expansion of space, some regions may recede so rapidly that their light will never arrive. It is critical to understand that this horizon is not a wall or a fence. It is a limit of perception, a boundary of measurement, not of existence. Just as the horizon on Earth appears to mark a limit beyond which one cannot see, but in reality continues endlessly, the observable horizon marks the limits of what we can currently detect, not the limits of the universe itself. The cosmos may extend far beyond, potentially infinitely, a vast expanse that lies permanently beyond our observational reach. If we consider the universe as the totality of space and time, then by definition it has no external boundary. There is no outside into which it can expand, no cosmic void that envelops the universe like air around a balloon. Expansion is a property of space itself, describing how distances between points increase over time, not how space grows into a pre-existing emptiness. This concept is profoundly challenging, because human experience is steeped in embedding. Every growth we witness involves something growing into something else. Waves spread across water, flames expand into air, and explosions push against surrounding material. Cosmological expansion, however, operates according to entirely different rules. The boundary of the universe is not a physical barrier, but rather a horizon of interaction, a constraint imposed by the finite speed of light and the geometry of space-time. The balloon analogy helps to visualize this subtlety. Picture a two-dimensional being confined to the surface of a balloon. As the balloon inflates, every point moves away from every other point. The being perceives expansion, yet there is no center on the surface, and stepping off the edge is meaningless within the being's geometry. The surface has no boundary, it is complete and self-contained. In the same way, for humans within our three-dimensional universe, the notion of an external outside is irrelevant. The universe's geometry is internally defined. It is complete within itself. Expansion occurs throughout this self-contained space, increasing distances between objects without reference to an external void. Mathematics allows for the conceptualization of boundaries in certain scenarios, especially in curved or finite spaces, but these boundaries do not resemble walls or edges in the usual sense. A closed spherical universe, for example, possesses a finite volume yet no boundary. If one were to travel in a straight line, eventually one would return to the starting point, having traversed the entire universe without ever encountering an edge. In such a universe, the total spatial extent is limited, yet accessible everywhere. No barrier obstructs motion, no edge halts progress. Even if the universe has such a topology, its curvature may remain invisible within our observable horizon, making it indistinguishable from infinite flatness when measured locally. This subtlety highlights the distinction between size and boundary, a distinction often lost in casual discussion. These considerations lead naturally to profound philosophical and scientific questions. If the universe has no edge, how do we meaningfully describe its origin? The Big Bang is often misrepresented as an explosion at a point in pre-existing space. In reality, it was an expansion of space itself, occurring everywhere simultaneously. Asking what came before the Big Bang, or what lies outside the universe, challenges the very concepts of time and space, for both are properties of the universe itself. In the framework of general relativity, space and time are intertwined into a single continuum, the fabric of space-time. Without space-time, the notion of a boundary ceases to have any meaning. There is no external container to hold the universe, no spatial frame to measure it against. The universe is its own reference. Observations continually push these questions to the forefront. Certain models suggest that space may be finite yet so vast that curvature cannot be detected within our observable horizon. Others propose exotic topologies, spaces that loop back on themselves in multiple directions, potentially forming a three-dimensional analogue of a torus or a higher dimensional manifold. In principle, these topologies could leave subtle signatures in the cosmic microwave background, such as repeating patterns or correlations on opposite sides of the sky. Researchers continue to search for these signals, testing the limits of both technology and imagination. To date, the data are consistent with a simple, flat, and possibly infinite universe. But the possibility of hidden curvature or a more complex topology cannot be entirely ruled out. Cosmic boundaries are further probed in the realm of quantum cosmology, where space and time themselves are subject to quantum effects. Some theories propose that time may be finite in the past, effectively removing the need for a sharp boundary at the Big Bang. In such models, the universe emerges smoothly from a quantum state, with no singular edge or initial point in the classical sense. Here, a boundary is not spatial but conceptual. It represents the limit of applicability of classical physics rather than a literal wall of space-time. These ideas stretch human intuition, suggesting that the origin and expansion of the universe operate according to principles vastly different from anything experienced in everyday life. These distinctions illuminate why cosmic boundaries resist simple explanation. They are not barriers or walls, they are horizons of observation, manifestations of geometry or thresholds of description. They redefine our notions of finiteness and infinity, forcing us to consider a universe that is complete, self-contained, and dynamic. The observable universe is bounded, yet the cosmos itself may be boundless. The edge is not a location, but a limitation in perspective, a line marking the frontier of knowledge, not the frontier of reality. As we grapple with these ideas, another question naturally arises. If space itself is expanding, what is the role of time in shaping this growth? Expansion is measured in terms of increasing distances between points as a function of time. The passage of time defines the horizon, governs the evolution of structures, and allows observers to witness cosmic history unfold. Without time, the very concept of expansion loses meaning. Time and space are inseparable, co-authoring the evolution of the universe and defining the framework within which horizons, curvature, and cosmological boundaries exist. Understanding expansion, then, requires a profound appreciation not just of geometry, but of the temporal dimension interwoven with it, a dimension in which the universe's history and future are continuously written. In conclusion, the universe has no edge in the sense of a tangible physical barrier. Its limits are determined by observation, geometry, and the interplay of space and time. Horizons mark what can be seen, while expansion occurs internally, stretching distances without a need for an external container. Finite or infinite, curved or flat, the universe is self-contained, revealing its secrets gradually through light, radiation, and gravitational influence. It challenges human intuition at every turn, reminding us that cosmic boundaries are conceptual and mathematical, not physical, and that the true scale of reality may forever surpass what our eyes and instruments can perceive. The universe's edge is not an edge at all, but the threshold of understanding, a frontier at which science meets both observation and the infinite. Time and space are inseparable in modern cosmology. Since Einstein's formulation of the general theory of relativity in 1915, the universe has been understood not as a static stage upon which events unfold, but as a dynamic fabric of space-time where geometry itself dictates motion. Matter and energy curve space-time, and this curvature guides the paths that objects follow. In this framework, space and time are woven together, forming an inseparable continuum. This union has profound implications. When we speak of the expansion of the universe, we are not merely discussing the increasing distances between galaxies. We are also describing the progression of time itself, intrinsically linked to the evolution of space. The two cannot be disentangled, for one exists as a function of the other. From the earliest instance after the Big Bang, this connection was fundamental. The Planck time, approximately 10 to the power of negative 43 seconds, marks the limit beyond which our current understanding of physics breaks down. Within this infinitesimal moment, quantum fluctuations dominate, and the smooth geometry of general relativity loses applicability. Yet from the Planck time onward, space and time began their intertwined unfolding. The universe did not expand into a pre-existing void. Rather, it was time itself progressing alongside the expansion of spatial dimensions. To ask into what space expanded is equivalent to asking where time passed before the existence of time itself. The very notions of before and outside lose their meaning at this scale, revealing the profound conceptual shift required to comprehend cosmic beginnings. Observations throughout the cosmos continually reinforce the deep bond between space and time. When astronomers observe galaxies billions of light years away, they are simultaneously looking back across both space and time. A galaxy 10 billion light-years distant is seen as it was 10 billion years ago, a period when the universe was far younger, denser, and expanding at a different rate than it does today. In this way, looking across spatial distance is inseparable from looking across temporal history. The Hubble constant, which quantifies the rate of cosmic expansion at present, is not fixed in time. It evolves as the universe ages, reflecting the continuous interplay between spatial growth and temporal progression. The cosmic microwave background, CMB, offers a particularly vivid illustration. This ancient light, emitted when the universe was only 380,000 years old, does not merely map the distribution of matter and energy in early space. It provides a snapshot of ancient time itself. The photons that we detect today have travelled across the expanding universe for over 13 billion years. Their wavelengths stretched in tandem with the expansion of space. Each measurement of the CMB is simultaneously a record of both distance and duration. In the subtle anisotropies, the tiny fluctuations in temperature across the sky, we observe the imprint of primordial conditions, frozen in a moment that combines spatial structure and temporal evolution. The passage of billions of years is encoded in the very fabric of the radiation we measure. The elasticity of time becomes even more striking when considered in the context of relativity. Near massive objects such as black holes or neutron stars, time slows relative to regions of weaker gravity, a phenomenon confirmed experimentally with atomic clocks at different altitudes on Earth. This demonstration of gravitational time dilation shows that time is not a uniform backdrop but a dynamic quantity, shaped by the curvature of space-time itself. On cosmic scales, the same principle applies. The evolution of time is tied to the expansion of the universe, to the density of matter and energy, and to the influence of dark energy driving accelerated expansion. Time unfolds alongside space, inseparable from the universe's dynamic geometry. This intertwining of space and time also shapes our understanding of cosmic limits. If space is finite, then time may also have a finite span, extending from a beginning to an eventual end. Conversely, if space is infinite, time may continue without bound, stretching forward indefinitely as expansion proceeds. The two dimensions are codependent. The evolution of spatial distances defines the framework for temporal progression, and the flow of time provides the canvas on which expansion occurs. The prospect of dark energy dominating cosmic evolution adds yet another layer. If dark energy remains constant, the universe will expand ever more rapidly, implying not just an ever-growing spatial expanse, but an endlessly unfolding future of time itself. Yet these are not the only possibilities. Some cosmological models entertain more exotic behaviours of time. Cyclic or oscillatory models, for example, propose that the universe may one day cease its expansion, collapse under gravity, and begin anew in a repeating sequence of big bangs and big crunches. In such scenarios, time itself could loop, with each cosmic cycle producing a new epoch, a new spatial domain, and potentially new laws of physics. Other models in quantum cosmology suggest that time may not be fundamental at all, emerging instead from more primitive quantum principles, much like temperature emerges from the collective motion of atoms. In this view, time is not a pre-existing dimension, but a construct arising from deeper layers of reality. The study of time and space together forces us to abandon the notion of an external frame of reference. There is no universal clock ticking outside the universe, no ruler against which distances are measured externally. Both time and space are properties intrinsic to the universe itself. Asking what lies beyond them is tantamount to asking what lies beyond existence as we can define it. The question challenges the limits of human intuition and the boundaries of language, requiring abstract reasoning and a willingness to embrace concepts that defy everyday experience. This recognition does not end inquiry. It deepens it, pushing science to explore not only what exists, but how the very notions of existence, duration, and distance emerge from the universe's own structure. Time's inseparability from space also informs our understanding of causality. Events in the early universe were intimately connected because they shared a temporal and spatial framework. The horizon problem, for example, arises from the observed uniformity of the cosmic microwave background. Regions of space separated by vast distances exhibit nearly identical temperatures, despite being causally disconnected under naive assumptions. Inflationary theory resolves this by positing that the early universe underwent a brief period of exponential expansion, stretching space and time together, allowing initially connected regions to influence one another before inflation dispersed them across the cosmos. The uniformity of the universe is, therefore, a testament to the intertwined evolution of time and space at the most fundamental level. Moreover, the link between space and time reshapes our understanding of infinity. If space is infinite, time may also extend without bound, and the universe may continue evolving forever, with stars burning out, galaxies drifting apart, and entropy steadily increasing. If space is finite, then the temporal dimension may also be constrained, with beginnings and ends that are difficult to conceptualize within human intuition. The interplay of dark energy, curvature, and initial conditions dictates not only the shape of space, but the ultimate trajectory of time. Every equation describing expansion, every observation of distant galaxies, every photon from the cosmic microwave background reflects this inseparable duality. In essence, the expansion of the universe is not merely a story of distances growing, it is the story of space-time itself unfolding. Time provides the rhythm of cosmic evolution, while space provides the stage upon which galaxies, clusters, and cosmic structures are distributed. Together, they form a continuum that defines existence itself. The progression of space cannot be separated from the flow of time, and the measurement of one inherently involves the other. To study cosmic expansion without accounting for temporal evolution is to view only half the picture. Ultimately, contemplating time and space as a unified entity illuminates the nature of the universe in ways that challenge both intuition and imagination. There is no external framework, no cosmic background against which to measure, and no absolute outside. Time and space exist because the universe exists. Their expansion, their geometry, and their evolution are self-contained. The questions of what lies beyond, what came before, and what lies ahead are constrained by this intrinsic unity. And as we probe the depths of cosmic history, from the Planck epoch to the accelerating expansion observed today, we are reminded that the universe is not simply a container in which events occur, it is a living, evolving fabric of space-time, and within it, every moment of time and every span of space are bound together in an eternal, inseparable dance. The idea of an infinite universe is one of the most challenging and provocative concepts in cosmology. If space is truly flat, as increasingly precise observations suggest, then one natural interpretation is that it extends without limit. In such a scenario beyond the observable universe, those roughly 46 billion light-years we can measure in any direction, there is not merely more of the same, but an endless continuation of galaxies, stars, and cosmic structures. There is no boundary, no edge, no terminal horizon. There is only more of the cosmos stretching outward without end, beyond the reach of even the most powerful telescopes or the longest conceivable journey. Infinity, in a physical sense, is profoundly counterintuitive. In mathematics, infinity is a well-defined concept, an unending series, an infinite set, or a value without bound. In equations, we can manipulate infinity, explore its properties, and understand its behavior within abstract systems. But when applied to the universe, infinity becomes tangible and awe-inspiring. It implies that every possible arrangement of matter and energy consistent with the laws of physics could exist somewhere. In an infinite cosmos, there could be another planet identical to Earth, another star system precisely mirroring our own, another individual who is an exact copy of you. The sheer scale of such repetition defies imagination, yet mathematically, it is a natural consequence of unbounded space. From a scientific perspective, infinity cannot be observed directly. We can measure only a finite portion of the universe, the observable universe, and even that is immense beyond ordinary comprehension. What we can do, however, is infer from geometry. The cosmic microwave background, CMB, mapped in exquisite detail by the Planck satellite, provides a window into the universe's large-scale shape. Tiny fluctuations in the CMB reveal the curvature of space. If the universe were positively curved, like a sphere, light travelling across vast distances would converge, altering the observed pattern of fluctuations. If it were negatively curved like a saddle, light would diverge, producing a different pattern. Observations indicate that the universe is flat to within a fraction of a percent, a precision that strongly suggests, but does not absolutely prove, spatial infinity. The remaining possibility is that the universe loops back on itself, forming a finite yet unbounded topology so vast that curvature is undetectable within our observable horizon. The idea of infinity also finds a natural home within inflationary cosmology. In the first tiny fraction of a second after the Big Bang, space expanded exponentially in a process known as cosmic inflation. Inflation smooths out irregularities, drives the universe toward flatness, and can stretch a small primordial region into a cosmos of enormous scale. Some models suggest that inflation did not end uniformly everywhere. Instead, it continues eternally in some regions, producing a so-called eternal inflation scenario. In this picture, our observable universe is just one bubble in an unending cosmic foam, surrounded by countless other regions undergoing similar expansion, each with its own laws, particles, or constants. Infinity is, in a sense, built into the very mechanism that shaped the universe. Yet the concept of infinity introduces deep scientific and philosophical challenges. In an infinite universe, the total mass energy would also be unbounded, complicating the mathematics of cosmology. Probabilities, which are central to physics, take on unusual properties. If the universe is infinite, even events with the smallest non-zero probability occur infinitely many times. A rare quantum fluctuation, a highly improbable alignment of stars, or even an improbable biological outcome could repeat endlessly, somewhere in the uncharted depths of space. This raises questions about the meaning of chance, uniqueness, and causality in a cosmos without limit. Philosophically, infinity unsettles notions of individuality and identity. In an unbounded universe, our observable patch is merely a tiny fraction of an immense, possibly unending whole. Each star, planet, and galaxy we observe is replicated innumerable times across vast stretches of space. Identity becomes a fluid concept. What does it mean for something to be rare if somewhere else it exists infinitely many times? What does it mean for an event to happen only once if infinite copies occur elsewhere? Infinity forces a reconsideration of scale, perspective, and meaning, even as it leaves local laws of physics intact. Despite these paradoxes, many cosmologists embrace infinity as the simplest explanation. A universe without boundaries aligns elegantly with observations and avoids introducing artificial constraints. It fits naturally with flat geometry and the predictions of inflation, and it does not require additional mechanisms to define an edge or boundary. Infinity becomes the default assumption. Unless observations indicate otherwise, it is the natural extension of a flat, homogeneous universe. From a theoretical standpoint, it provides a simple, unbroken continuity that matches the data and minimizes the need for arbitrary constructs. Nevertheless, infinity is not the only conceivable possibility. The universe could be finite yet unbounded, looping back on itself in ways that defy simple visualization. In this case, traveling in a straight line could eventually bring one back to the starting point, much like circumnavigating the globe. Higher dimensional analogues, such as a torus or other exotic topologies, could create a universe that is vast but not limitless. Such a structure would have no edges yet would contain a finite volume. Researchers continue to search for subtle patterns in the cosmic microwave background, looking for repeating imprints that might reveal the topology of space. These patterns would provide a rare glimpse into the global shape of the cosmos, offering a window into whether infinity is literal or only apparent. The implications of an infinite universe extend into cosmology's most speculative realms. If infinity is real, it suggests the plausibility of a multiverse, in which our universe is only one bubble among countless others. Each bubble could have different physical constants, dimensions, or initial conditions, producing an unimaginable diversity of realities. Infinity, in one sense, the spatial infinity of our universe, hints at infinity in another, the multiplicity of universes, each obeying its own version of physical law. In this context, our universe is not the entire cosmos, but a finite glimpse within a boundless ensemble of possibilities. The infinite universe is both intellectually compelling and emotionally disorienting. It is simple to describe: no edges, no limits, an endless continuation of space. Yet grasping it stretches the imagination beyond ordinary experience. It challenges us to think not in terms of containment, but in terms of ongoing extension, not in terms of singularity, but in terms of repetition and unbounded variety. For astronomers and cosmologists, infinity is both a practical assumption and a profound mystery, a framework that explains observations while simultaneously pointing toward realities that may forever elude direct measurement. In the end, contemplating infinity forces us to confront the vastness of the cosmos and the limitations of human perspective. Our observable universe, enormous as it is, may be a mere fragment of a larger, unending continuum. Infinity opens the door to paradoxes, philosophical reflection, and speculative possibilities, reminding us that the universe, and our understanding of it, is far richer, stranger, and more expansive than intuition alone can capture. And as compelling as the idea of an infinite universe is, it inevitably leads us to the even broader question of the multiverse. What if the infinity we observe is just one part of an even greater cosmic ensemble, extending in ways that challenge the very definition of existence itself? The notion of a multiverse extends cosmology beyond the boundaries of a single universe. Instead of treating our observable cosmos as the entirety of existence, multiverse theories suggest that what we perceive may be just one region among countless others, each governed by its own conditions and potentially its own laws of physics. This idea is not the product of science fiction, but arises naturally from attempts to address profound questions in modern physics. Observations have revealed remarkable fine-tuning of the constants of nature, an extraordinary near flatness of space, and evidence of an early phase of rapid cosmic inflation. Each of these puzzles, when considered within a conventional single universe framework, presents a degree of improbability that hints at a larger context, one that the multiverse concept seeks to provide. One of the most compelling routes to the multiverse comes directly from inflationary theory. In the first fractions of a second after the Big Bang, space underwent an extraordinary period of exponential expansion. In many models of inflation, this rapid expansion does not end everywhere simultaneously. Instead, pockets of space cease inflating, forming isolated bubble universes, while inflation continues elsewhere. Each bubble evolves independently, with its own initial conditions and physical constants, eventually forming galaxies, stars, and planets within its domain. Our observable universe could be just one such bubble, existing within a broader inflating background that remains forever beyond our observational reach. In this eternal inflation scenario, the multiverse is not an optional speculation. It is an inevitable consequence of the very physics that drives inflation itself. A second path to the multiverse emerges from string theory. String theory, an ambitious framework attempting to unify all fundamental forces, requires additional spatial dimensions beyond the familiar three of space and one of time. These extra dimensions are compactified or curled up in a myriad of ways, each configuration giving rise to a different set of physical laws in the resulting universe. Some configurations may favour a strong gravitational force, others a weaker one. Some may allow certain particle masses, while others produce entirely different particle spectra. The sheer number of possible compactifications is staggering, producing what is often referred to as a landscape of universes. Within this landscape, our universe appears as one particular realization amid an enormous, perhaps infinite ensemble of possibilities. Quantum mechanics offers yet another route to the multiverse. The many-worlds interpretation, proposed decades ago by physicist Hugh Everett, suggests that every quantum event, the decay of a particle, the spin of an electron, the outcome of a measurement, branches into multiple outcomes, each realized in a separate parallel universe. While this interpretation remains controversial and cannot yet be empirically confirmed, it illustrates how the fundamental laws of quantum physics naturally give rise to a vast ensemble of realities. Each possible history unfolds somewhere in this cosmic web, producing a multiverse in which every potential outcome exists. One of the most significant motivations for considering a multiverse is the apparent fine-tuning of our universe. The constants of nature, the gravitational constant, the strength of electromagnetism, the cosmological constant, and others, appear remarkably well suited for the emergence of stars, galaxies, and life. Even small deviations in these parameters could render a universe sterile, incapable of forming complex structures. In a single universe framework, this precision seems almost miraculous. In a multiverse, however, fine-tuning is no longer improbable. If countless universes exist, each with different constants, it becomes inevitable that some will have the precise conditions necessary for complexity to arise. Observers like us would naturally find themselves in one of these life-permitting universes, a selection effect sometimes referred to as the anthropic principle. Despite its conceptual appeal, the multiverse raises profound challenges. By definition, regions beyond our observable horizon lie beyond direct measurement, making empirical confirmation exceedingly difficult. Critics argue that if a concept cannot, even in principle, be tested, it may lie outside the domain of science. Proponents counter that indirect evidence could someday be attainable. For example, collisions between bubble universes in the early stages of inflation might leave subtle imprints in the cosmic microwave background, the faint afterglow of the Big Bang, though no such evidence has yet been definitively observed. The multiverse remains speculative, but it emerges naturally from theories that have already proven remarkably successful in describing our own universe. The multiverse also reshapes our understanding of cosmic expansion. In a single universe picture, the question, what is the universe expanding into, is already challenging to answer, but in a multiverse context, expansion might occur within a larger inflating background. Our bubble grows, distances increase, and galaxies recede from one another, yet the space beyond may itself be inflating, unseen and inaccessible. This perspective does not resolve the ultimate question of an outside, but it reframes it, suggesting that our universe is embedded within layers of reality far beyond direct observation. Even if the multiverse remains speculative, it has become a serious subject of study not because physicists pursue exotic fantasy, but because established theories, cosmic inflation, string theory, and quantum mechanics, point naturally in its direction. The mathematics of inflation predicts bubbles. String theory allows a vast landscape of possible universes. Quantum mechanics suggests branching histories. Taken together, these frameworks imply that the cosmos we observe may be only one island in a far larger archipelago of existence. Whether the multiverse exists in reality remains uncertain, yet its consideration deepens our understanding of expansion, of the limits of observation, and of the nature of reality itself. And even within the bounds of our own observable universe, without invoking other realms, a profound mystery continues to dominate cosmology. Dark energy, the unknown force accelerating cosmic expansion. The multiverse may provide context for why our universe has the properties it does, but the fundamental question remains: what is driving the cosmos to expand at an ever-increasing rate, and how does this force shape the fate of all that exists within the universe we can observe? Dark energy is one of the most profound mysteries in cosmology, a force that reshapes our understanding of the universe on the larger scales. In 1998, two independent research teams studying distant Type Ia supernova, exploding stars that serve as standard candles for measuring cosmic distances, made a startling discovery. The expansion of the universe is not slowing under the pull of gravity, as had been long assumed, but accelerating. This revelation upended decades of cosmological assumptions and demanded the introduction of a new component of the cosmos, an energy inherent to space itself, exerting a repulsive effect that drives galaxies apart at an ever-increasing rate. Over the following decades, a wealth of observational evidence has confirmed this phenomenon with remarkable precision, from the detailed imaging of the Hubble Space Telescope to the extensive surveys of the Sloan Digital Sky Survey and the exquisite measurements of the Planck satellite. Dark energy is estimated to constitute approximately 68% of the total energy density of the universe, far outweighing the contribution of dark matter, which makes up about 27%, and ordinary matter, which accounts for a mere 5%. Despite this dominance, its nature remains profoundly elusive. The simplest and historically earliest explanation is the cosmological constant, introduced by Einstein in 1917 as part of his equations of general relativity. Originally conceived to maintain a static universe, Einstein abandoned it when observations revealed an expanding cosmos. Yet with the discovery of accelerated expansion, the cosmological constant returned to prominence, representing a uniform, unchanging energy density that permeates all of space. However, the cosmological constant is far from a complete answer. Quantum field theory, which describes the energy of the vacuum, predicts a value for vacuum energy that is staggeringly larger than the observed effect of dark energy, by as much as 120 orders of magnitude. This discrepancy is often called the worst theoretical prediction in physics, and highlights the profound gap between theoretical expectations and observational reality. For many physicists, this enormous mismatch signals that the cosmological constant, while useful, is likely only part of a more complex story. In response, alternative explanations have been developed. One prominent proposal is quintessence, a dynamic field that evolves over time, unlike the fixed cosmological constant. Quintessence could vary in strength across the history of the universe, potentially influencing the rate of cosmic expansion at different epochs. While current observations provide no clear evidence for such variation, the concept remains a plausible extension of the Standard Model, offering a mechanism by which dark energy might emerge from deeper physics. Other hypotheses suggest that dark energy may arise from modifications to general relativity itself on cosmological scales, implying that the familiar laws of gravity may require revision when applied to the universe as a whole. The influence of dark energy is profound and far-reaching. On scales of billions of light-years, it dictates the dynamics of cosmic expansion, ultimately shaping the long-term fate of the universe. If dark energy remains constant, as in the cosmological constant scenario, expansion will continue indefinitely, gradually separating galaxies until the cosmos becomes cold, diffuse, and dark, a state sometimes referred to as heat death. If dark energy strengthens over time, the acceleration could become extreme, ultimately tearing galaxies, stars, planets, and even atoms apart in a hypothetical scenario known as the Big Rip. Conversely, if dark energy weakens or reverses, expansion could slow, potentially leading to a future contraction, or even a cyclic cosmology in which universes undergo repeated phases of expansion and collapse. Each of these possibilities depends on the elusive properties of dark energy, which remain one of the most pressing mysteries in physics. Observational efforts to understand dark energy continue at an accelerating pace. Measurements of the cosmic microwave background, baryon acoustic oscillations, and distant supernovae refine our understanding of cosmic expansion. Future observatories, such as the European Space Agency's Euclid satellite and the Vera C. Rubin Observatory, are designed to probe dark energy with unprecedented sensitivity. These projects aim not merely to measure its effects, but to uncover its nature, whether it is a true cosmological constant, a dynamic field-like quintessence, or a manifestation of more fundamental physics yet to be discovered. Each observation provides a small piece of a larger puzzle, gradually illuminating the force that dominates the universe on the larger scales. Dark energy also reframes a central question about cosmic expansion. What is the universe expanding into? In the presence of dark energy, the answer is subtle but profound. Expansion is driven not by movement into an external void, but by intrinsic properties of space itself. Space stretches because of its own internal energy, and no external container is required. This perspective reinforces the view that the universe is self-contained. Distances between galaxies increase because the fabric of space itself is dynamic, not because it is moving into something beyond it. Yet even as dark energy clarifies why expansion accelerates, it leaves open a fundamental enigma. What is this energy, and why does it dominate precisely during the current cosmic epoch? Its existence appears finely timed, becoming significant only after billions of years of cosmic history. This coincidence, the why now problem, suggests that understanding dark energy may reveal deeper structures of reality still hidden from observation. Another crucial aspect is the scale dependence of expansion. On local levels, the influence of dark energy is negligible compared to gravity. Galaxies, clusters of galaxies, and even solar systems remain gravitationally bound and stable, unaffected by the stretching of the cosmos on larger scales. This contrast between local stability and global acceleration illustrates the subtlety of cosmic dynamics. Expansion is a feature of space itself, dominant over vast distances, yet invisible within the gravitationally bound systems we can study directly. It is a reminder that the universe operates differently across scales, governed by the interplay of forces that we are only beginning to comprehend. Dark energy, mysterious as it is, represents a fundamental frontier in cosmology. It challenges our understanding of physics, reframes questions about the universe's expansion, and forces us to reconsider the very nature of space and time. Its discovery has transformed our view of the cosmos, revealing a universe more dynamic and enigmatic than previously imagined. As scientists continue to probe its properties, dark energy remains both a driver of expansion and a symbol of the profound mysteries that lie at the heart of the universe. On the larger scales, galaxies recede from one another as space itself expands. Yet on local scales, this expansion has no measurable effect. The Milky Way does not grow larger with time, nor does the solar system drift apart under the influence of cosmic stretching. The difference lies in the balance between expansion and local gravitational binding, a subtle interplay that shapes the universe we observe today. Understanding this distinction is essential for grasping how the cosmos can simultaneously expand while preserving intricate structures like galaxies, stars, and planetary systems. Expansion is fundamentally a large-scale phenomenon. General relativity describes the geometry of space-time and shows that the metric of space evolves with time, increasing the distances between unbound objects separated by hundreds of millions of light-years. As a result, galaxies not bound together by gravity appear to move away from each other, their recession speeds increasing with distance in accordance with Hubble's law. However, within galaxies, stars orbit under the mutual gravitational pull of billions of neighbouring stars, and within solar systems, planets remain tightly bound to their parent stars. In these locally bound systems, gravity completely overwhelms the gentle effect of cosmic expansion. Space may be stretching everywhere, but these structures resist that stretching entirely, maintaining their cohesion over billions of years. This principle explains why galaxies within clusters remain connected, even as the clusters themselves move apart. The local group, for example, contains the Milky Way, Andromeda, and several smaller galaxies. These galaxies are gravitationally bound strongly enough that their mutual attraction dominates over the expansion of space. In fact, the Milky Way and Andromeda are on a collision course, expected to merge in roughly 4.5 billion years. Expansion does not interfere with this process. Instead, it only becomes relevant at distances where the gravitational ties between objects are too weak to resist the cosmic stretching. In general, on scales under roughly 10 million light-years, local gravity dominates, effectively decoupling these regions from the global expansion of the universe. Astronomers quantify this separation of scales using the concept of the Hubble flow. Beyond a certain distance, typically hundreds of millions of light-years, the motion of galaxies aligns with the general trend of expansion, described by the Hubble constant, which measures the rate at which the universe grows. Closer in, however, peculiar velocities, motions driven by local gravitational interactions, dominate. Some nearby galaxies, for instance, move toward us rather than away, drawn by the gravitational pull of the Milky Way or local galaxy clusters. Only when one looks across vast intergalactic distances does the smooth, predictable pattern of cosmic expansion clearly emerge, revealing the large-scale structure of the universe and the underlying influence of dark energy and space-time dynamics. This separation of scales is critical for understanding cosmic structure and evolution. It explains why galaxies, stars, and planets could form despite the rapid expansion of the early universe. If expansion dominated on all scales, matter would never have condensed after the Big Bang. Instead, the gravitational attraction between particles and gas clouds overcame the subtle stretching of space on small scales, allowing matter to clump, collapse, and eventually form the complex structures that populate the cosmos today. In this way, gravity sculpted the details, while expansion provided the broad framework within which the universe could grow. The coexistence of these two forces, local binding and global stretching, is what makes the cosmos both structured and dynamic, simultaneously stable and evolving. Observations of the cosmic microwave background provide a vivid illustration of this interplay. Tiny density fluctuations imprinted in the early universe served as the seeds for gravitational collapse, while expansion stretched space between them. Over billions of years, this delicate interplay produced the cosmic web, a vast network of filaments containing galaxies and clusters, separated by immense voids of relatively empty space. Within each filament, gravity has played the dominant role, pulling matter into complex structures. Between filaments, expansion dictates the large-scale geometry and separation, ensuring that galaxies are carried apart as the universe ages. The contrast between local stability and global expansion also explains why human-scale objects are entirely unaffected by the universe's growth. At the level of atoms, molecules, planets, and even stars, electromagnetic and nuclear forces dominate, making the influence of cosmic expansion negligible. Expansion is not a force that disrupts molecular bonds or planetary orbits. It is a property of space itself, observable only across immense cosmological distances. Recognizing the distinction between local and global effects is crucial to avoiding common misconceptions. Expansion does not occur selectively between galaxies while leaving them themselves untouched. Rather, space expands everywhere, but the effects are entirely overwhelmed in regions where other forces, primarily gravity, hold sway. The universe's expansion is thus both pervasive and subtle. It stretches the large-scale framework of the cosmos, while allowing smaller systems to remain intact, creating a universe in which intricate structures can exist within a dynamic, growing environment. This distinction also raises deeper questions about the ultimate fate of the universe. How far can expansion continue, and under what circumstances might it dominate over gravitational binding on all scales? The answer depends largely on the balance between gravity and dark energy, the mysterious component of the cosmos driving accelerated expansion. If dark energy continues to dominate, galaxies not gravitationally bound will recede beyond the reach of observation, ultimately isolating local groups like the Milky Way and Andromeda in vast empty voids. Conversely, if the influence of dark energy changes over time, or if gravity somehow regains dominance, expansion could slow, and the large-scale structure might evolve differently, potentially reversing in some cosmological scenarios. Each possibility hinges on the same fundamental distinction. Local forces maintain cohesion, while global expansion governs the universe's large-scale evolution. Understanding the interplay between cosmic expansion and gravitational binding is therefore essential, not only for interpreting the structure of the present universe, but also for predicting its future. It frames how astronomers measure distances, interpret redshifts, and model the growth of structure. It explains why galaxies, clusters, and planetary systems exist, and why they are not torn apart despite the relentless stretching of space. And it sets the stage for contemplating the long-term evolution of the cosmos, where local stability and global expansion together define the ongoing story of the universe. The fate of the universe has long captivated both scientists and philosophers. Since Edwin Hubble's discovery of cosmic expansion in the 1920s, the question of how the universe will end has evolved from speculation to a precise scientific inquiry. Whether the cosmos continues to stretch forever, slows to a halt, or reverses into collapse depends on the interplay between matter, radiation, and the enigmatic force known as dark energy. Each possibility leads to a profoundly different cosmic destiny, shaping the ultimate narrative of existence itself. In the early 20th century, cosmological models considered primarily matter and radiation. If the density of matter were high enough, gravity would eventually overpower the initial expansion, slowing it and ultimately reversing the process. In this scenario, known as the Big Crunch, galaxies would first decelerate in their recession, then begin to fall back together. Stars and galaxies would collide and merge as the universe contracted, culminating in a state of extreme density and temperature, potentially similar to conditions at the Big Bang. The Big Crunch held an appealing symmetry for theorists. A universe that begins in a fiery explosion might end in a fiery collapse, a cosmic echo of its birth. Conversely, if the density of matter were too low to halt expansion, the universe would continue to grow indefinitely, though at a decelerating rate. This scenario, often called the Big Freeze, envisioned a universe that cools eternally as galaxies drift farther apart. Stars would exhaust their nuclear fuel, galaxies would fade, and black holes would slowly evaporate through Hawking radiation over unimaginable timescales. Eventually, matter itself might decay, leaving behind only a diffuse sea of photons and elementary particles scattered across ever-expanding space. In such a universe, the arrow of time continues, but all processes gradually fade into a cold, dark uniformity. The discovery of accelerated expansion in 1998 radically altered these predictions. Observations of distant Type Ia supernovae revealed that the universe's growth is not slowing under gravity, but accelerating. This required the introduction of dark energy, an unseen component of the cosmos that drives galaxies apart with increasing speed. Dark energy's dominance shifted the most probable outcome toward eternal acceleration. The Big Freeze now occurs not merely as a gradual cooling, but as an accelerating process. Galaxies beyond our local group will eventually recede faster than the speed of light, vanishing from view entirely. Over immense timescales, the night sky will grow emptier, until only the remnants of our own galaxy remain observable. A lonely cosmos stretching into infinite darkness. An even more extreme scenario is the Big Rip. If dark energy's strength increases over time, its repulsive force could grow without bound. At first, it would tear galaxies apart, overcoming the gravity that binds them. Later, It could disrupt the cohesion of star systems, ripping planets from their orbits. Eventually, it might overcome atomic and even subatomic forces, disassembling matter itself. The timeline for such a fate depends on the precise properties of dark energy, which remain uncertain. Yet if this scenario unfolds, the universe would end not in quiet cooling, but in catastrophic disintegration, a violent unravelling of every structure from galaxies down to atoms. Other models suggest alternative outcomes. The Big Bounce, for instance, proposes that the universe might collapse and then re-expand, creating a cyclic pattern of death and rebirth. Quantum cosmology adds nuance, suggesting that a collapsing universe could tunnel into a new expanding one through quantum transitions, linking successive cosmic cycles. In these models, the Big Bang was not the ultimate beginning, but one of many rebirths in a grand sequence. The universe becomes a dynamic system, eternal in its transformations, rather than a one-off creation and destruction. Some theorists even consider these scenarios within a multiverse context. In eternal inflation, while our universe may face a big freeze or a big rip, other regions of space could undergo entirely different fates. Some bubble universes might collapse, others might inflate endlessly, each following its own set of physical laws. In this view, the multiverse contains all possible endings, repeated infinitely across unobservable regions. Our universe's fate, then, is only one story in a vast ensemble of cosmic narratives. The difficulty of predicting the ultimate fate of the cosmos lies largely in the mystery of dark energy. If it behaves as a cosmological constant, unchanging in strength over time, eternal acceleration and the big freeze appear most likely. If it evolves, outcomes like the Big Rip or even future contraction remain possible. The challenge lies in measuring its properties with enough precision to distinguish between these scenarios. Upcoming surveys and observatories, including the Vera C. Rubin Observatory and the Euclid satellite, aim to probe dark energy in unprecedented detail. These efforts hope not only to map the expansion, but to understand its underlying cause, potentially revealing new physics beyond the standard cosmological model. Whichever fate ultimately unfolds, it is inseparably tied to the same question that defines the beginning. What does it mean for space itself to expand? Cosmologists must consider not only the large-scale structure of the universe, but also the fundamental laws that govern its growth. General relativity provides a remarkably accurate description of expansion, yet when combined with quantum mechanics, inconsistencies arise, particularly at the earliest times and extreme energies. Resolving these inconsistencies is not merely a theoretical exercise. It could reveal the deeper mechanisms controlling expansion and illuminate why the universe has evolved the way it has. This challenge leads directly to the pursuit of quantum gravity, the unification of general relativity and quantum mechanics. Understanding quantum gravity could reveal whether the universe expands into anything at all, or if expansion is a self-contained feature of space-time itself. It might explain why the cosmos began in a hot, dense state, why it continues to grow, and how dark energy fits into the grand picture. Could expansion be an emergent property, arising from deeper quantum processes, rather than a fundamental motion into some external void? These are the questions driving the next frontier of cosmology, bridging the observable universe with the ultimate laws of nature. In contemplating these possibilities, one begins to appreciate the profound subtlety of cosmic evolution. Expansion is not merely a stretching of distances, but a dynamic feature of the universe itself, intertwined with time, energy, and the deepest laws of physics. Its ultimate outcome, whether quiet dissolution, violent disassembly, cyclic rebirth, or something beyond imagination, remains uncertain. Yet each scenario flows naturally from the same principles that govern the cosmos today, inviting us to explore not only the fate of galaxies and stars, but the very structure and meaning of space and time.